you just throw the cat?
Onto the bed. There's a bed
Okay.
right here.
I'm scared.
So yeah. She's all right. She's all right. Okay, guys. So yes, today we are going to carry on where we left off last time, which was yesterday, and we're gonna finish chapter 3, chapter 4, and then go some way into chapter 5, if not the whole thing, and then we're gonna start doing some practice stuff, some other like practice final exams and whatever we have to do. So to pick up where we left off, we didn't quite finish partial fractions yesterday, right? So partial
Recording? Are we there?
fractions.
Are you there?
I'm recording. Can you say something quickly? There we go. Thank you. Yes, we are good. We are good.
Okay.
Everything's in the
Great.
recording. So we're gonna pick up here from partial fractions, and so gotta get the actual. We're gonna find some example questions quickly to do. Yeah. Okay. So let's just do another example quickly, and then I think we'll do one more example, and then we will do the practice, the mini test. I mean, we're gonna do the mini test for it. So the example I have from the textbook here is the integral of x squared plus 3x plus 5 over x plus 1 dx. So it's a ratio of functions of polynomials, so we can do partial fractions on this. One thing we can do is divide right away. Actually, polynomial divide this, so let's do that quickly. So x squared plus 3x plus 5 divided by x plus 1. So it's going to be, what do I multiply x by to get x squared? I multiply by x all the way around. X squared plus x, subtract. It's going to be 0. 3 minus x is 2x, and then the plus 5 goes there. What do I multiply x by to get 2x? Multiply by 2. 2x plus 2, subtract. 2x plus 2 is going to be 0, 3, plus 3. So what that tells us is that this can turn into, so that's equal to x plus 2 plus 3 over x plus 1. Is that it? Yeah, x plus 2 plus 3 over x plus 1. Oh, so this isn't a partial fractions question. It's just a division question. That's all it is. But anyways, it's part of the same chapter, so good to note anyways. So now we can integrate this pretty easily, right? We can integrate this. This is going to be x squared over 2 plus 2x plus 3 ln absolute value x plus 1 plus c.
Like this. And then it has like a white stuff on the top.
Oh, is someone talking to me, or is someone? I think someone just has their mic on.
Mm-hmm.
Let's see who it is.
No.
Sohail, I think you have your mic on.
No, blue.
Thank you. Okay. So let's see. So this is just the first example. This is just our, not even a what's it called question? Partial fractions questions. But it's good to just know how to divide. So if anyone has any questions about dividing, ask me now.
I have just a question about these in general.
Sure.
Have we ever gotten, I don't know, we might have gotten one, not for a mini test, but maybe as a homework question, like, what are they called? Initial value question, where you have to find C after we have an integral?
Not after we have an integral, but after we have a differential equation. Yeah, okay. In the differential equations, we did do that. Yeah, that was in chapter 4. So we will get to that today.
Okay, that was on the mini test, wasn't it?
Yeah, it was. Any differential equation pretty much has an initial value, unless it's not an initial value problem, but most of them are. So, Okay, next example. I'll do this one, and then we're gonna do the mini test one after. So the integral of 2x minus 3 over x cubed plus x dx. How are we doing on people? Do we need another streamer, or are we okay? We are okay right now. Okay. So first things first, can I divide this? No, because the degree here is less than the degree on the denominator. So factor the denominator. Well, that's not too hard. It's going to be x times x squared plus 1. X squared plus 1 is an irreducible quadratic factor, so dx. So what I have to do now is I have to turn 2x minus 3 over x times x squared plus 1 into some sum of fractions. So the first one is going to have the linear factor, just a, and then the second one is going to be, it's a quadratic factor, so I have to put bx plus c over x squared plus 1, right, over x squared plus 1. Now we have to figure out what a, b, and c are. So multiply both sides by the denominator here. And we're going to get 2x minus 3 equals a x squared plus 1 plus bx plus c times x. Okay, so we're going to get 2x minus 3. 2x minus 3 equals ax squared plus a plus bx squared plus cx. So what do we learn from this, right? Well, we learned that 3 different equations, right? I can write this as 0x squared plus, so we learned that, actually I guess in one more step, 0x squared plus 2x minus 3 equals a minus b, no, a plus b, x squared plus c x plus a. So a plus b is equal to 0. C is equal to 2. A is equal to negative 3. Right, so a equals negative 3. C equals 2. And a plus b equals 0. So from this, we can say that negative 3 plus b equals 0. So b equals negative 3. Nope, b equals 3. B equals 3, yeah. Okay, so then we have our 3 solutions. So that means that this fraction, this 2x minus 3 over x squared plus 1 can be written as a over x plus bx plus c over x plus 1, x squared plus 1. Okay? And then now we can integrate both sides instead, right? Instead of integrating the left side, we can just integrate the right side. So this is going to be negative 3 ln absolute value x plus, okay, now I'm going to do u sub, so integral of u equals x squared plus 1, du equals 2x dx. So this is going to be, I want 2x here, so it's just going to be 1/2. Oh no, it's 2x plus 2. Whoops. Yeah, sorry, I'm not quite ready for the u sub. So I have to separate this out into 3x over x squared plus 1 plus 2 over x squared plus 1 dx. Now this is negative 3 ln absolute value x times plus, not times. Now I do the u sub. So u equals x squared plus 1, du equals 2x dx. And so now I'm going to take the 3 out and divide it by 2. And then it's just going to be 1 over u du. Yep, that seems right to me. Plus, plus 2 times, and now what's this integral here? Well, 1 over x squared plus 1, if we again look at our calculus 1 notes, yeah, that's going to be tan inverse. So it's going to be 2 times 1 over a is 1, so 2 times 1 over 1 tan inverse of u over a, which is just x squared over 1. So there we go. And now we are just one step away. So negative 3 ln absolute value x plus 3/2. That's going to be the integral of 1 over u is ln absolute value x squared plus 1 plus 2 tan inverse x squared plus c.
Wouldn't it just be tan inverse x? Because that's how the integral for 1 over x squared plus 1 is?
Yeah, let's see. Yeah, you're right. It would just be x. Thank you. Yeah. There you go. So that's the integral. Let's just make sure that's right. 3/2 ln x squared plus 1 plus 2 tan inverse x minus 3 ln x plus c. Yep, that's good.
Where did you get the 3 over 2 from?
The 3 over 2 came from, so I'll write it properly here, 3 over 2. So the 3 comes out from here. That's where the 3 comes from. And then the over 2 comes from the u sub, this 2 right here.
Oh, okay.
Make sense?
Yeah.
There you go. Okay, so then there's that. Let's try the mini test question now then. Whoops, did not mean to do that. I just have to open it in a new window. I have it saved here. So this is going to be mini test Yeah, this is going to be mini test 3. So my mini test 3 question, so I'll say mini test number 3, is going to be, well, or was, x squared plus 2x over, now it's going to be 3x minus 1 squared x minus 7 dx. So luckily they give us the denominator already factored, right? They give it already factored. So we can right away start working on the partial fractions here. So x minus 7. One thing to notice is that we're not able to divide because this denominator has a power of 3, a degree of 3, and this numerator has a degree of 2. And also our factors are linear, except this one appears twice, so we have to do something special when they appear twice. It's good that it's here because then lets me do it. So let's first deal with the x minus 7 factor. That's just going to be, it's linear, so it's just a over x minus 7. Now for the 3x minus 1, this is how you deal with it. It's still linear, so you put a constant on the top, and you put it once to the power of 1, and then you put it again, 3x minus 1 squared. That's how you deal with it when it appears twice. So this is what it means for a factor to appear twice, is that it's squared there, right? It's a factor with twice the, it's a different property, but you know, a algebraic multiplicity, is that what it's called? Algebraic multiplicity of 2, yeah. And those have special things, so this is the special case with that. You put it twice like that. So now to deal with this, still I'm going to multiply both sides by the denominator. So I'm going to get x, wrong color, x squared plus 2x equals, what's over here? Well, it's going to be a times 3x minus 1 squared plus b times, well, it's going to be 3x minus 1 times x minus 7 plus c times x minus 7. Right, so let's deal with this side here. I'm going to have to, what am I going to have to do? I'm just going to have to expand that. I just have to. So it's going to be a times 9x squared minus 6x plus 1. Yeah. Plus b times 3x squared minus 21x minus x. So minus 22x. Yeah, minus 22x. Minus, no, plus 7 plus cx minus 7c. And now multiply all that in. So 9ax squared minus 6ax plus a plus 3bx squared minus 22bx plus 7b plus cx minus 7c. And now finally, I'm going to group the x squared term. So 9a plus 3b x squared plus the x terms. It's going to be negative 6a minus 22b plus c. The x terms. Right, I got all the x terms? Yeah. And then the constant term, which is just, well, which is negative set. Well, do it from the left. So a plus 7b minus 7c. Okay, and this is equal to x squared plus 2x plus 0. So this is going to be 9a plus 3b is equal to 1. Negative 6a minus 22b plus c is equal to 2. And a plus 7b minus 7c is equal to 0. So we have a plus 3b equals 1. Negative 6a minus 22b plus c equals 2, and a plus 7b plus c, sorry, minus 7c equals 0.
Isn't it 9a plus 3b? You forgot the 9.
Yeah, you wrote them. Yeah, it's 3a plus b equals 1.
It's also 9 here, and then where is it?
No, that's right.
That's right. Oh, okay, that was a mistake. Okay, sounds good. Thank you. Yeah. Let me just check this is what I had. 3a plus. This is not what I had. Did I make a mistake? This is not what I had when I was solving the question. 7. Yeah. What did I do? Oh, no. Hold on. Yeah, let's see if... I don't know if I did it right or wrong yet. So, I'm going to solve this with... There is another way to solve this, of course, which might be faster. And I'm realizing now I should have... it's a good... I forgot about this other method to do it. So, okay, we can solve the system, but I will mention the other method. So, we can solve the system, and we'll get equations out. But there's another way to do it. So, if I get this equation right here... Right, if I get this equation right here... Right? And so I'm going to say here, this is other method to solve, right? So if I go here and I say choose x equals 7, what's going to happen? Well, it's going to be 49 plus 14 equals a times 21 minus 1 is 20 squared plus 0 plus 0. There's an x minus 7 term in there. 0 plus 0. So what that lets me do is it lets me solve for a quicker. Right? I get a. So it's going to be 49 plus 14 over 20 squared. And I get 63 over 400 for a, which is not what I got before. So 63, I got that for C. That's weird. Oh yeah, no, that's okay. Never mind. Yep, because when I did, so I shouldn't be comparing to what I did before because I did it slightly different. I ordered the numbers wrong. No, that's fine. It is correct, so we're good. 63 over 400. It's just that it's called C on my solution here. Yep. So there we go. We got A, and now I can choose another. Well, can I actually choose another variable? I can't quite choose another variable because you see here, if I were to sub in. No, if I were to sub in, actually, I could solve for C. If I were to sub in, well, what does 3x minus 1 equals 0? So it's going to be x equals 1 over 3, right? So if I sub in x equals 1 over 3, then what do I get? Well, I get 1 over 9 plus 2 over 3 equals 0 plus 0 plus cx minus 7. Oh, and by x minus 7, I mean 1/3 minus 7. So I can solve for C now pretty easily. It's going to be...
So a good way to look for this is probably if you have factors that appear twice, you probably want to check if you can do this easily.
Yeah, this is a good time to do that, yeah.
Mm-hmm.
Minus 7. So I get C is negative 7 over 60. C equals negative 7 over 60. So we have A. Let me highlight what we have. We have A. We have C. I'm just missing B. And to solve for B, well, I can just choose one of these equations if I want. Like, these still apply. These ones here, they still apply. So I'll just take the first equation, I guess. 9A plus 3B equals 1. So if I want to solve for B, it's going to be B equals negative 9A. Oh, no. 1 minus 9A. So equals 1? Yeah. 1 minus 9A over 3. A is 63 over 400. So 1 minus 9 times 63 over 400 over 3. I get negative 167 over 1200. I know these numbers look weird, but they are right. They are correct. So there we go. We have B now. Negative 167 over 300. Can't change it now. And there we go. So now what that tells us is that I can write this as, so the fraction that we had originally, which was x squared plus 2x over, well, you know what, I'll just highlight this and bring it down quickly. So what this means is that I can rewrite this as saying it's equal to A, 63 over 400, 63 over 400 over x minus 7, plus B, so I'll say minus 167 over 1200 over 3x minus 1, plus C, so minus 7 over 60 over 3x minus 1 squared. And I can integrate this instead of the other side. All right, is there a question? Maybe no? Okay, someone's got their mic on. Someone check. Ooh, their mics. Everybody do mic check. Okay, sounds good now. So I will from here, I'm going to integrate the right side here instead of the left side. So if I integrate this, let's see what we can do. Well, so the first term here is going to just nicely be 63 over 400 ln absolute value x minus 7. Next one's going to be minus
would it be 167 over 1200 times 3 or something, or no?
That's right. That's right. Times 3 ln absolute
Ln.
value. Yeah, 3x minus 1. Just it's a u sub. Just try the u sub with this one. You're just gonna multiply by 3. So 1200 times 3 is 3600, of course. And then minus. Okay, well then this one we have to deal with. Minus 7 over 60 times the integral of 1 over 3x minus 1 squared. Okay, so Erwin, could you mute because you're.
Oh yeah,
That's the other question. Yeah.
My question is, so you know how you did like when you have 1 over something and you can just turn it into the ln of that thing?
Yeah.
So does that only work when the thing on the bottom is like a degree 1 polynomial, correct?
Yeah.
So if it's like x squared minus 7, then it won't work.
Then you have more trouble.
You have to do, what's the method called again? This one.
Partial fractions? This right
Yeah,
here?
partial
Right?
fractions.
Yeah. You might have to. Yeah. Probably have to.
Okay.
Or not. Well, not probably. There are lots of other methods to deal with it, but.
Yeah. Okay, I think that's pretty much it. Also, 2 more things.
Yeah.
So do you know what time we're finishing at today?
I have this listed to go until 10, so sometime between now and 10.
Okay. Yeah. Okay, that's good. And also, you might want to call someone else because it's like 48 people. Like it's not there, but like it's pushing the limit. So you might want to call someone.
Sure, I'll just mention
start
it.
streaming if it needs to be.
Oh, okay. Then yeah. Then
right
if you see it's 50, if you could start streaming, that would be nice.
I'll
Yeah,
start
thank you.
streaming now. I'll just
Okay, sure. Yeah.
preventative.
Yeah. Thank you very much. That's very good. So now to deal with this over here, how do we deal with this integral? Well, 3x minus 1, I could say, oh yeah, all I have to do, actually it's not that hard. So all I have to do is u equals 3x minus 1, du equals 3 dx, right? So this is going to end up being, okay, well, 63 over 400 ln absolute by x minus 7 minus 167 over 3600 ln absolute value 3x minus 1. Okay, and now this is going to be 1 over 3, so negative 7 over 3, right, or 3 times 60, which is 180, so 180, integral of 1 over u squared du. Okay, so the integral of 1 over u squared is not too hard to do, because that's just u to the negative 2, right? And so now this is just going to be, well, this whole thing, which I'll just copy and paste. Minus 7 over 180 times, okay, add 1 to the exponent, so it's going to be u to the negative 1 divided by the new exponent. So there you go. That's going to turn this into a positive, and this is going to be over u. U was 3x minus 1, so 3x minus 1, and there plus c. And let's see if that's the same answer that I got. So negative 167 over 3600 ln 3x minus 1, 63 over 400 ln x minus 7, 7 over 180, 3x minus 1 plus c. Yep, that is correct. So yeah, that is
So
that.
you said the other method was just a linear system, so put it in like a matrix and then just RR, yeah. Okay.
That's right. You'd get the same numbers at the end.
You know, these questions seem a lot easier going over them a second time.
That's true. Yeah.
Maybe I just sucked at math before.
Well, I think it's like everything, for me at least in math, is like I need the time to process it, right? Like the first time I took calculus in high school, I wasn't doing that good in high school. So like the first time I took calculus, I did reasonably bad. I guess I got a 70 the first time I took calculus, which is not very good, but like it's okay, not compared to at least now the math we're doing. But it was like the first time I'm like, obviously the first time I'm learning calculus, and it went too fast for me, and I just like didn't have the time to process it. And then when the course was finished, I could do derivatives, I could do everything totally easily. But it was after the course was finished because I just needed the time to process it. So it's similar like this stuff is like, we can do this stuff. I mean, how I feel at least is that I can do this stuff now, no problem at all. But when I was first learning it, it's just that it's so fresh, you don't have like, your mind didn't process it enough. So even if you're not consciously thinking about something, I think once you learn it, in the background of your brain, you're processing it. And so now this has had enough time to process, and so it comes much easier to deal with this stuff. But it's always good to refresh, of course. Okay, anyways, that's
Cool
my
insight there, bud.
little
Cool
insight
insight.
here. Okay,
Of course,
Yep.
of course.
Can you scroll up for a second?
It's really like simple. Like you just like you have the polynomial over like factors, and then you just have to like, and you just have to like break it up, and then
Yeah.
It's not-
okay, someone's asking a question though? Someone,
I
yeah.
didn't get
yeah.
the question. Like, I never got this when we were learning it the first time, but when there's like in the scroll down a bit to the
Yeah.
question we just did.
This is the end here
Like
though.
the 3x
Yeah.
squared minus 1, or the 3x minus 1 squared,
Here?
and
Yeah.
the x minus 7. When you did the A, B, C thing,
Mhm.
you did like in the denominators, it's x minus 7, 3x minus 1, and then 3x again minus 1 squared.
Yeah.
Why isn't the last one 3x minus 1?
Yeah. So you're asking like, how did I get these like terms right here, right? This
No, I
that
got how
and
you got the first two, just not the last
Yeah.
one.
the last one. Well, yeah, I don't particularly have a good explanation for it. It's just that the rule in general is just the number of times that this appears, so it appears twice, you need to do exactly like I did it here. You show it the linear factor once with something on the top, and then the linear factor twice with something on the top. And if this showed up 3 times, if for example it was 3 here, then you'd have another term, d over x 3x minus 1 cubed. You have a third term like that. So for every like power of the exponent here, for every power of the linear factor, that's how many times it needs to appear, and each time the power needs to go up by 1. The reason that works, and the reason any of this works, and like the reason like that we can do this and there always is a solution is not something that this course is like, we don't have an answer for that in this course. But I guess the point of this course is just to learn how to do it, which is like this. So
Okay.
does that make sense? Like how to do it, like just for each thing like that.
Yeah.
Take a look in this discussion. I just put a screenshot from the textbook.
Yeah.
That put outlines like how to break it up.
Yeah. There is a general problem-solving strategy for it, which is here. Yeah, thank you for sending that. It's a little bit hard to read, I'm going to be honest, but well, I guess this one isn't actually that bad. It's a little hard to read, but even when Horowitz did it, it was difficult to understand. I think it's much easier to understand just in an example, and just see what I mean when I say this. Like, it appears twice, so there's 2 times there, and yeah. A question?
So like, so when you have like when it appears twice, you just have to do one factor where it appears once, and then one factor where it appears twice. It's like kind of like here, right?
Yeah.
So is that the rule?
Is that what? Sorry.
So like whenever you have a factor that appears twice, like squared, you have to have a factor. You have to have a b over e to the power of 1 and c over power of 2.
Yeah.
And if it's like let's say 3, would it be the same thing, but just like d
Yeah.
over that?
Yeah,
over
d
3?
over x 3x minus 1 cubed.
So is there any like reason behind it, or is that just like a rule we have to follow?
Yeah, that's what I was saying before. Yeah, we don't have an explanation for why this all works in this course. We don't have, that's probably something for real analysis that if you want.
No, that's probably something for 3 blue, 1 brown.
Yeah, that
Amir
definitely is.
explained it in his videos.
Yeah.
Amir explained it. Yeah, Amir explained it in his videos. If you go watch it.
Okay, so there you go.
There's the answer is go watch a video if you want.
Yeah, go watch a video if you want to learn how to. I can't explain it right now. So yeah, although I'm interested in why it works, I just haven't looked it up yet. So yeah. So anyways, that is the end of partial fractions. We're gonna move on to 3.7 now. So 3.7 is improper integrals. Can't remember if it's an M or an N. In, open my notes quickly. I have to actually open my notes anyway, so it's fine. LaTeX 3.7 improper integrals. No, that doesn't make sense. Wait, I'm confused now. Is it? I'm the English question here. Is it improper? Improper. It's M.
It's
Oh,
improper.
okay. Again, I swear I can spell. It's just when I'm on camera, for some reason, I can't spell.
It's okay, Adam. You're an engineer. It's okay.
I'm nervous to make a mistake that's just on the screen. So, integrals.
It's okay, Adam. You're an engineer. It's okay. You know, you just have to say I'm an engineer.
Exactly. No need to spell here. Okay, so is there a question quickly before I start 3.7? Okay, sounds like no.
Ask.
Yeah.
How many questions are on the exam? Did they tell us how many questions they're going to be?
How many? Either 5 or 6.
Yeah.
5 or 6.
Oh, that's it.
If you go to the final exam place on D2L, I think there's a details page that tells you that information.
Yeah. So
okay, thanks.
So essentially, there's 2 main parts to this section. It's this picture right here. Okay, that's the first part. So let me look at that for a second and try to understand. And then whoops, that's not what I meant to do. And then this one, which is a little bit longer, but these are the 2 things to understand. If you understand these 2 pictures, then you understand 3.7. So first one is, how do you evaluate an integral with infinity at its bounds? Well, what you do is you split it, right? So you see right here, this next line, we split it at some point A, right? We split it, and that point A can be anything. It can be anything. It's usually 0, unless you have a reason to not choose 0. So that point A is where you split the integral. You say, well, integral from A to negative infinity plus the integral from A to infinity. And then, well, you can't really evaluate the integral at infinity or negative infinity. So you say, well, the limit as some variable goes to infinity or negative infinity. And they have to be different variables. Notice it's t here and r. But essentially, if you want to evaluate this, then it's this. And I think you can probably understand how to deal with it if it's probably like if it's like 8 here, right? Then it's just 8 on the here. That stays, and you just take the limit as that goes up. Okay, so that's the first part. So that's the first kind of improper integral, and there's another kind of improper integral, which is I should be clear. Assuming the limit exists. If the limit doesn't exist, then it's divergent. If the limit does exist, then it's convergent, and it converges to some number. We use this in an integral test in chapter 5. We use this thing here. So then the second part of it is if there's a discontinuity between the bounds, right? If there's a discontinuity between the bounds, the light turned off. 1 second. It randomly turns off because it thinks it hears clapping. So if there's a discontinuity between the bounds, then you can't integrate over that discontinuity. You're gonna have a problem. So let's say at C, right? If we have at C there's a discontinuity, then if I want of f of x, then if I want to integrate from A to C, then I have to take the limit as some variable approaches C from the correct side, right? So if I'm going from a lower bound, if the upper bound is our discontinuity, it's going to be C from below. And then otherwise, if it's the other way, if it's from C to B, then I have to approach C from above. Okay, then together we can conclude a formula for integrating a function with discontinuity within its limits, with a discontinuity within its limits of integration, using the same f of x as right here. So if we're going from A to B, and C is between A and B, right? C is in between A and B. Then if you want to integrate that, then you have to do this, right? So approach it from either side, split the integral at C, split the integral at C, and approach it from either side and see what happens. If either of these don't exist, if the limits of either of these don't exist, the whole thing diverges.
Okay, I have a question.
Yeah.
So I never really understood about these chapters. Like, why do you have to do this whole thing with limits? It's like these, because I understand you have to do it, but I'm getting the idea when. Because I know, whether if you do from A to T, for example, of f of x, you're going to get function at the end. Let's just say x squared plus 5, right? But then when you sub t back in, you're going to treat t as if it's negative infinity. So aren't you? Why do you have to like assign? Why do you have to put a limit? Why can't you just like?
Why can't you just sub in infinity? Like sub in infinity?
Yeah, why do you need to do a limit for it?
You can do that. You can do that if you want. It's not very like I think a math major would have trouble with that, but I don't think an engineering major should have trouble with that. So yeah, I think that you can do that.
Isn't that essentially what you're doing in the end of the day? Because that's how I always thought it.
It is what you're doing. You're just subbing in infinity. It's just that you can't actually sub in infinity. Like numbers don't work like that. But yeah, even when you sub in infinity, like you can say in some way you can say like, yeah, we're technically just subbing in infinity. But you can also look at it like this: when you sub in infinity, you're technically just taking a limit, right? You're like that's pretty much what you're doing. You're not actually subbing in infinity. You're taking the limit as the function goes to infinity. So really, no matter what, you're doing a limit, right? That's the only way to actually evaluate this is with the limit.
Limits are it's the fundamental basis of calculus. So it lets us take either very small pieces or very large pieces of something.
Correct. Yeah.
So everything we do in calculus is taking the limit of something.
Yeah.
I mean, that's what a derivative is. But
isn't that what
simplify it by using like our techniques and stuff?
Exactly. Yeah. So
because I know that. Because I know that technically every derivative you take could just be done with the h or f of x plus h plus or minus f of x over h. Like everything could be done like that. It's just like it's very long. Yes.
Well, you'll notice now that because we've done chapter 5 and chapter 6, an integral is basically the limit of a series.
Mm-hmm. That's true. That's why we had that definition for integrals in Calc 1.
We use limits to evaluate a lot of things in calculus without really knowing it.
Yeah.
Okay. Anyway, thank you.
Like even the question that someone asks, like, why do you do the limit to infinity? It's because we don't know what's going to happen to infinity, but we want to know what happens as we go to infinity.
Exactly.
Like infinity is forever, so yeah, that's why.
There's nothing at infinity because you can't be at infinity. You just can approach infinity. Right? Yeah. And this is just I put on the screen just to like emphasize like what we're saying. Yeah, like everything in calculus is based on limits. Even like the definite integral is defined in terms of a series, a limit of a series. We did this in Calc 1, if you don't remember. And yeah, you can kind of see where our notation comes from. This is kind of like this whole thing replaces the integral sign, and this is kind of like our dx. So when you take the limit as n goes to infinity, it turns into the integral from a to b of f of x dx. And yeah, there you go. Okay, anyways, that's that. Let's do some practice here with these questions. I'll erase that. Gotta find it now though. Improper integrals. So let's try. Scroll through it a little bit here. Okay, let's try this one. The question is evaluate the integral from negative infinity to 0 of 1 over x squared plus 4 dx. Okay, so, well, we can look here. And so this is going to be, one of my bounds is infinity. So I can turn this into the limit as t goes to negative infinity of the integral from t to 0 of 1 over x squared plus 4 dx, right? Well, I can write this as 2 squared, so this is now the tan inverse one. So this is equal to the limit as t goes to negative infinity of 1/2 tan inverse x over 2, right? Evaluated from t to 0. So evaluated at 0, that's just 0, pretty sure. Is that 0? Yeah, evaluated at 0 is 0. Tan inverse of 0 is 0. Yeah, 0. So that's fine. So I can say this is going to turn into the limit as t goes to negative infinity of, okay, evaluated 0 is 0, minus 1/2 tan inverse of t over 2. And this limit you can try to figure out. I mean, if I go onto the calculator, I think this is something we're supposed to know. So if I say arctan x, limit as x goes to negative infinity, looks like it's approaching something. What exactly is it approaching? It's approaching y equals pi over 2, but negative. It's approaching pi over 2, negative pi over 2. That's just something you're supposed to know, I think. I remember Horowitz doing this question and asking, are we just supposed to know that? He said yes.
So like it's just supposed to be memorized. It's like
I guess
how does that come to like mind?
It's not really memorization, because if you think about a normal tan function, right? It has its bound, like the first cycle of it has its bound from negative pi over 2 to positive pi over 2. And when you're taking an inverse function, you can only take the first cycle of it, right? Of a trigonometric function, right? So when you're flipping it, you're kind of thinking that the domain is now the range of the first cycle there. That's how I end up remembering it. Because that's basically what you're doing.
That's true.
So that first thing, it just kind of rotates and then, mirrors against y equals x, and then you get that.
Yeah. So you see here, that's the idea.
One trick
that's some thinking, but yeah.
I know other people use, but one trick I would always use for these types of questions is I just do in my calculator arctan of 9999999 a bunch of 9 divided by 2, and see what spits out. If I see that it's like pretty close to like some known value, like a constant, that
yeah, exactly. My calculator actually even gives it to me in radians. It says, oh, that's close enough to infinity, so I just call it pi over 2.
Geez, and then you have the big calculator.
Yeah. So
do
yeah.
Do you water cool it?
Do I what?
Tan is.
Do you water cool it? Like that's.
Oh yeah, no, I don't. I don't water cool it, no. But I might need to.
Tan is just the ratio of the two sides of a triangle. So
yeah.
the largest ratio you can have, or it's the angle, but like the largest ratio you could have would be 1.
Yeah, with pi.
If you get more than 1, then you get a weird triangle.
Okay, so let's see. So we know that this limit is pi over 2 now. So this is just going to be equals negative 1/2. So this evaluates to pi over 2. So, sorry, negative pi over 2. So pi over 2, which gives me pi over 4 as our answer. What? Tan inverse. Wait, tan inverse. What's tan inverse of 0? Is it 0? Yeah, tan inverse of 0 is 0. What? Negative?
Yeah, the third one is correct. I don't know what's wrong.
Oh, the 1/2 is not supposed to be there. Why is there a 1/2 in the start? No, that's not what it is. No, I think this might be a mistake.
Is the formula right?
No, I think this one actually, let's see, integrate 1 over x squared plus 4 from negative infinity to 0. Pi over 4. Pi over 4 is the answer. It's pi over 2 in the textbook, but pi over 4 is what we got, and that is the answer. So yeah, there we go.
The textbook disappointed me.
Textbook is wrong in this case, yes. There you go. Okay, so that's that question. That's how you do it. You take the limit like that. Let's do a discontinuity one.
Adam, are you getting these questions from the textbook?
Just straight from the textbook, yeah. From the in the chapter, yeah. Okay, let's see here. I have let's do this, I guess. So the next example I have, and it's probably the last example for this section because I do want to move on, is integrate from 0 to 2 of x ln x dx. Okay, where's the discontinuity? Well, we have a discontinuity at 0 because ln of 0 doesn't exist. So what we have to do is we have to then integrate this. So the limit as t approaches 0 from above, right? We're going from above, approaching 0, times the integral of, not times the integral, but limit of the integral from t to 2 of x ln x dx. Okay, well now we have to integrate x ln x. So x ln x, I'm gonna have to do probably integration by parts. Yeah, so I'm gonna do that on the side here. I'm gonna do an indefinite integration by parts here, dx. So u equals x. Yeah.
Can't you just do a u substitution, or would that not work?
What would I choose for u?
Oh no, you can't because it's ln there.
Yeah. Sorry, dx here. Du equals dx. V equals, what's the integral? No, sorry, I want to differentiate. Yeah, other way around. I want to use, I want my u to be ln x, and I want my dv to be x, dx. Because then my du is 1 over x dx, and my v is x squared over 2. Yeah. So now that this integral is going to be equal to uv ln x, x squared over 2, right? Plus the integral minus the integral of v du. So x squared over 2 times 1 over x is going to be x over 2. Move the over 2 to the other side. X dx is going to be x squared over 2 plus c. Plus c doesn't matter. So it's minus 1 over 4. I did that kind of fast, so hopefully the point of this isn't to do integration by parts. So if you're iffy on that, go look at integration by parts. But yeah, unless you have a question, I'm happy to answer any questions here. But yeah. So now that's our integral. I'm going to say, well, the limit as t goes to 0 of this evaluated at, so ln x, x squared over 2 minus x squared over 4, evaluated from t to 2. So this is going to be the limit as t goes to 0 from the top of, so ln 2 ln 2, 2 ln 2 minus 1, minus ln t squared over 2 minus t squared over 4. Okay, well, this is going to stay. We just have to see if any of this stays. So the limit as, see if I have this right, t squared ln t plus 1. Yeah, everything's right here. Oh, okay.
I have a question.
Yeah.
Isn't it isn't it just the ln t squared over 2 minus t squared over 4? Isn't that just 0? Because 0 over 2 is just 0.
But what's
And
ln
you're
what's
taking the
ln
positive.
0?
But you're taking it from the upper side, so it wouldn't. Yeah, I don't know.
Yeah,
It's just, it doesn't. It won't matter because you're still gonna be multiplying by 0. So it's just 0.
That's true, but technically it's infinity times 0, which is indeterminate. Which is, sorry,
Yeah.
negative infinity time the ln of 0, the limit as t goes to 0 from the right of ln t is negative infinity. So you'd have negative infinity times 0, which is L'Hopital's rule. You have to do L'Hopital's rule on that.
Can't we not just do that?
Yeah, we will. We will do that. Exactly that. Minus 2 minus ln. So these constants can come out of the limit. So these can come out. So it's 2 ln 2 minus 1. Okay. Minus the limit as t goes to 0, 0 from the right, of ln t. I'll take the 1/2 out as well. I can't take the 1/2 out quite yet, but yeah, ln t squared over 2 minus t squared over 4, like that. Okay, well, this is 0, right? This is 0 pretty clearly. So this is going to be 2 ln 2 minus 1 minus the limit as t goes to 0 from the right of ln of minus 1/2 ln t over t to the negative 2. Right? So now I have to evaluate this limit. I'll do it with L'Hopital. So with L'Hopital, it's going to be 2 ln 2 minus 1 minus 1/2 times the limit as t goes to 0 from the right of 1 over t minus, the exponent goes down, minus t to the minus 3. Yeah?
How did the t get down? Cause it 2t squared. How did it get down?
But it's t to the minus 2 here now. T to the minus 2.
How did it become from 2 to minus 2?
Because I put in the denominator.
Well, how do you just put it down there?
Like x is equal to 1 over x to the minus 1. So t squared is equal to 1 over t to the minus 2. The minus exponent just means it's in the wrong spot. So this is equivalent still.
Okay, my bad. Thank you.
Right?
Adam?
Yeah?
Didn't you have t squared over 2? Where'd the 2 go?
Here.
Oh,
can
you
move it outside the limit, yeah.
Oh, and then you also forgot when you're taking the derivative of the bottom, it's supposed to be negative 2 times t.
You're right, yeah, that's true. I don't know where that went.
Oh.
Yeah, thank you. That's good. Okay, so then now we evaluate this limit. So it's going to be 2 ln 2 minus 1 minus 1/4, actually plus a fourth. Limit as t goes to 0 from the top of, well, 1 over t, I'll just write it fully, 1 over t over 1 over t cubed. So that cancels with one of those. So it's just going to be 2 ln 2 minus 1 plus 1/4. Limit as t goes to 0 of t squared, which is 0. So 2 ln 2 minus 1 is our answer.
I don't know if this applies. Oh, I'm sure this applies in some spaces, but I think it was either Majid or CPW who said, like, if you just compare how quickly ln t would decrease and how quickly what was it, just
T squared?
T squared goes to 0 faster than ln t goes to negative infinity.
Yeah, that's true.
Which is why we end up getting 0.
Yeah. But if you want to show it, you show it with L'Hopital. But yeah.
Yeah, but to show you can't just kind of guess. Again, to be like, oh,
you don't know
guess.
for sure. You don't know for sure.
No, you don't know for sure. He was just saying that, like, in general, that's what you should expect.
To get an idea of where to go.
Like, if whatever one has the higher order is most likely going to be the one that you get.
Yeah.
So any squared beats any like logs or exponents?
I mean,
any
so.
logs?
To get to 0, yeah.
Yeah. Okay, thank you.
Okay, well that's 3.7. Yeah, go for it.
Sorry, just to clarify. So we do integration by parts, and then we take like the limit.
We do integration by parts, and then we take the limit. Yeah, as t goes to 0. That's right.
Oh, alright.
The only reason that you put the t squared in the denominator was so you could do like the hospital or the however you say it.
L'Hopital,
right?
Yeah, you do L'Hopital. Yeah, that's right. That's why I did that. Because it has to be a ratio of functions like that. Okay, so that's 3.7. Yeah, question?
Was there a mini test for this one or no?
There was not a mini test for this one.
Oh, okay.
So that's it for chapter 3. So if there's any questions in chapter 3, ask me now. You can ask me later too, but it's good to ask it now. So I'll take 10 seconds while I'm looking for the next one. Anybody can ask a question.
So what would you say is like the most important kind of like things that I would keep in mind? Because like I know it's a big chapter and it's like many things to keep in mind. But what would you say is like some? Because like I know this is like a very kind of analytical chapter where it's a lot more like tricks to like just get the right answer somehow.
Yeah.
So like how would you say it's like some general rule that like you should kind of look at when you see a problem, when it's not necessarily like those obvious things to kind of you see a problem like and you're like, I don't know how to take this.
Yeah, see like I guess see how you can factor things. So for partial fractions, I mean, like, you know, make sure you're factoring everything as much as you can and canceling. Remember that if you have a plus b over c, this is a over c plus b over c. You can do that. That comes in handy a lot when you're integrating. And then remember in integration by parts, like if you can split, like we had an example which was x to the 7 square root of 1 plus x to the 4. This whole thing doesn't have to be your u, and this whole thing doesn't have to be your dv. It could be, you know, you can split this into x cubed and x to the 4 and x cubed, right? And this can be your dv, and this can be your u, right? Which is how you actually solve this problem. And so things like that, like factoring and splitting things up in unexpected ways, that's very useful in this section. Like this is another example of splitting things up in not super apparent ways.
So if let's say you go on the test, like one of the questions has some like big integral that kind of is not necessarily obviously in a category, just a factor or do something later factor.
Yeah, it's gonna be a partial fractions, or it's gonna be an integration by parts question.
This chapter is they can combine a lot of chapters into one question for this chapter.
Yeah.
Because you can do
Sadly.
proper integral with like a trig function and a trig substitution.
That's right.
They can do all that in one.
Yep.
Anyway,
and I wouldn't be surprised if that's one.
It's Horowitz, you know. Just expect the worst. It's Horowitz, you know.
Yeah, I guess so. So the next question is separable differential equations. And so that's in chapter 4. So it's our first section in chapter 4. The first bit of this is just a bunch of definitions about differential equations. So not relating to separable ones just yet, because you have to know what a differential equation is first. Differential equations are the main application in engineering and stuff like that of calculus. Maybe I don't know if that's entirely true, but pretty much the main application of calculus in engineering is solving differential equations. So this is our first time. It's just that to do that, you have to be able to differentiate and integrate and all that kind of stuff. So this section, so we have a bunch of definitions here. So a differential equation is just an equation where x, y, y prime, and all the derivatives, or any number of the derivatives, that include it. So the equation includes these things, right? A solution is a function where you can sub it in, and it makes the equation true. Okay, and then the order of a differential equation is the highest derivative. A general solution is something we'll talk about soon, but a general solution is like with a c, right? So integration, remember, leaves a c there. And so the c can be any value, and that means you can have a whole family of functions as your solution. And then an initial value problem is where it's not a c. You have to solve for what c actually is, and there's a specific initial condition that you have to apply, that you have to solve for. And so not a family of functions, a specific function with specific coefficients and everything. A really good way to think about it, I mean, how I think about it is like, if we had like, you know, like x plus 2 equals 3. Very simple linear equation. We can solve for x pretty easily here, right? But if I have, you know, x squared plus 2x plus 3 equals 5, well, we need the quadratic formula to be able to do this, right? We have other ways to do it too, but mainly the quadratic formula is the easy, the most straightforward way. So very similarly, if I had like dy by dx equals, I don't know, 2x squared plus 5, yeah, you can solve for y here pretty easily. Just integrate both sides with respect to x, right? You can solve that pretty simply. But what if I gave you y dy dx plus 2 equals dy d squared y by dx squared plus dy by dx, well, times x. How would you solve for y now, right? That's pretty hard. I mean, this is a second order differential equation that we don't know how to solve yet. So this is something that you want to solve with something like a quadratic formula. It's just that you're not solving for a number here, you're solving for an actual function that satisfies this equation. And that's the idea of solving a differential equation. Okay, so there's just the ideas of solving differential equations. Someone's got their mic on, could they mute? And then, so separable differential equations are the first kind. And so it's like we're learning a quadratic formula. We're learning a formula to solve a specific kind of problem. Just like the quadratic formula solves this specific kind of equation, we're learning a specific kind of differential equation that we're able to solve. And so a separable differential equation is an equation written where you have y, oh my god, can I write y? Y equals, y prime equals f of x times g of y. And so essentially the idea here is that you have the derivative of y is a function of x, right? And you can separate what is, like, it's equal to something, and that function can be separated to an x part and a y part. So to solve this, what we essentially do to solve this differential equation is we write dy by dx here, f of x, g of y. Oops, g of y, right? So we want to solve for y equals, right? We want to solve for y equals. So to solve this, we essentially do this. So it's going to be divide both sides by g of y and multiply both sides by dx. So it's going to be 1 over g of y times dy equals f of x dx, and then integrate both sides. And so this is how we solve it. On the right side, you're going to get some function with a y in it, right? And then solve for y, rearrange to solve, isolate for y, and that's your answer. Now, of course, some people may notice that I use the differential as a fraction, which is not actually entirely how you do it, but a lot of that happens a lot in differential equations, where you use this as a fraction to solve the differential equation. There is a way to use them as fractions, but that's pretty advanced. So for now, you just have to say, okay, well, I could use it as a fraction here, but you're never asked to do that yourself.
Wait, can you scroll up a second?
Scroll up, yeah. Higher?
No, that's fine. All right, thank you.
No problem. So let's take a look at some example problems. So a separable, separable differential equation. So let's say, for example, I have the first example in the book here is y prime equals x squared minus 4, 3y plus 2. So to integrate this, we're going to use this formula. Sorry, not to integrate. To solve this differential equation, we're going to use this formula right here. And so we have, it's going to be 1 over 3y plus 2 dy integral equals the integral of x squared minus 4 dx. Again, just using this formula here. I separated into f of x. This is my f of x. And this is my g of y. Right? And so 1 over g of y dy integrated, and then integral of f of x dx. Now I actually do the integration. It's going to be 1/3 ln absolute value 3y plus 2 equals x cubed over 3 minus 4x plus c. Now I can't forget the plus c here, because when I'm rearranging for y, I need to take into account the plus c. But the question only asks for, find the family of solutions. Find the family of, or the general solution, which means I leave it as a c. I don't know what it is. So I just leave it as a c. And I just rearrange for y with that as a c then. So let's do it. So it's going to be ln absolute value 3y plus 2 equals x cubed minus 12x plus 3c. And then e to the power of both sides. So it's going to be 3y plus 2, sorry, absolute value of 3y plus 2 equals e to the x cubed minus 12x plus 3c. E to anything is always positive, right? E to the anything is always positive. No, that's not true. Yeah, it is. Never mind. It is true. And yeah, so, yeah. And so the absolute values do nothing. Absolute values don't do anything. So now it's 3y, well, it's already 3y plus 2. And so then I can isolate for y by just subtracting 2 and then dividing by 3. So y equals 1/3 e to the x cubed minus 12x plus 3c minus 2. And there we go. That is our solution to the differential equation. So, any questions about what I just did there?
3c is c, correct?
What'd you say, sorry?
3c, c is the same as c.
Yeah, pretty much. I mean, it just depends where you call c. I mean, I could right now say d equals 3c, and now I replace everywhere with a d, and it's a different. It's just a constant. It doesn't matter.
Yeah, and also, don't you have to add the c when you integrate, like, with y, or no?
No, you only need one c, because like I could put a c here, but then I can just move this c over, and I can just define that as c.
So
remember, it's just some constant. It doesn't matter.
If you put one, there is one. You just like it's already included.
That's all you need. You just need the one c. That's all you need.
Right. Thank you.
Wait, for a separable differential equation, right? In the question they'll give you a y prime, right?
Well, no, they'll give you exactly like something we have up here. Like.
So yeah, like on the left side there's a y prime. Like that's.
Oh, I see what you mean. Like yeah. You might have to do a little bit of rearranging. You might have to do more, some rearranging to get it into this form. We'll do an example like that after this. But not too much rearranging, I don't think. I don't think they'll give you that much. Let's see an example. Okay, so there isn't quite an example.
Adam.
see. Yep.
Could you real quick just go over it a bit, just the starting part.
Yeah, starting part here. So like how I go from
Yeah.
this line to the next line?
Yeah.
Yeah. So remember the formula is if I have something in this form, right? Something in this form, which is y prime dy by dx is equal to f of x, some function of x, times some function of y, g of y. Right? If that's true, then I can rearrange it to become this, and this will let me solve the differential equation. So the integral of 1 over g of y dy equals the integral of f of x dx.
Okay, got it.
Make sense?
Yep. I just missed that part when you were explaining it.
Yeah, don't worry about it. Don't worry. Yeah. Okay, so that is this example. There actually isn't more examples in the book that are actually good examples. So I guess I'll do one more. Yeah?
Real quick, could you explain how you got 1 over 3y plus 2?
1 over 3y.
Yeah,
sorry,
plus 2 in the second line. Yeah.
Oh, he's talking about the g of y.
Yeah, the g of y. Yeah.
Oh yeah. Well, because this is g of y here, 3y plus 2. And so the formula is to do 1 over g of y. So g of y is 3y plus 2.
Oh, okay.
This is just 1 over
I
g of y.
Yeah, I didn't catch that. But...
Yeah. Okay, so let's do this. Let's do this here, and we will see what we're doing. So, sorry, 1 second here. Okay, I have another one with an initial value, so I'll write it here. Y prime equals 2x plus 3 y squared minus 4, where y of 0 equals negative 3. Okay, so it's already separated. That's f of x, that's g of y. So I know I can write this as the integral. This is another example here. The integral of 1 over g of y dy equals the integral of f of x dx. So this right side is y squared minus 4. So I'm going to have to look at my Calc 1 formulas. And the Calc 1 formulas are telling me nothing useful. Y squared minus 4.
Very relatable.
I don't think that's any like of the sine, cos, tan integrals. I think
I mean,
just
if you
have to
took
do
it,
that normally, like
unless you make it,
Oh, partial
could,
fractions?
That's in the form of never.
isn't. Go ahead.
X squared minus a squared.
Yeah.
Yeah.
What has the antiderivative x squared for x
Hey,
minus a
can't you
Or
guys
why
do
don't you just factor out the denominator? So y plus 2, y minus 2, and then you do partial.
Yep, that's probably what I'm going to do. Yeah. Y plus 2, y minus 2.
Like, don't you do u sub where like u equals y squared plus minus 4? Can't you do that?
But then you need to have a y up here. You need to have a y here. Because your derivative of this is 2y, right? So you need to have a y in the numerator to do that. But there's no y.
Yeah.
Right. So yeah, this is the, well, times the integral equals the integral of 2x squared over 2. So x squared plus 3x plus c. And now I have to integrate this side here. I guess no plus c yet, but integrate this side over here. So yeah, so 1 over y plus 2 y minus 2 equals a over y plus 2 plus b over y minus 2. 1 equals a y minus 2 plus b y plus 2. Okay, I'll sub in y equals 2 here. So it's going to be 1 equals 4b. So b equals 1 over 4. And then, so this would say y equals 2. Y equals negative 2. So it's going to be 1 equals negative 2. So it's negative 4a. Minus 2 cancels that out. So it's going to be a equals negative 1 over 4. So that tells us that this can be turned into the integral of negative 1 over 4 over y plus 2 plus 1 over 4 over y minus 2 dy. So that equals, still right here, x squared plus 3x. This is going to be negative 1 over 4 ln absolute value y plus 2 plus 1 over 4 ln absolute value y minus 2 equals x squared plus 3x. Okay, now we have this to solve for y.
Wait, where did the c go?
Yeah, I need to put a c now. Now that I finished integrating, I'll put a c. I'll put a c on the right side here, plus c. So I'll write it again just so we see it better. 1 over 4 ln absolute value y plus 2 plus 1 over 4 ln absolute value y minus 2 equals x squared plus 3x. Okay, so I need to isolate for y here, right? So to get that going, well, first I'm going to multiply both sides by 4, and I'm going to switch the position of the first two. It's going to be ln absolute value y minus 2 minus ln absolute value y plus 2 equals multiplying by 4. So 4x squared, sorry, there's supposed to be a plus c here, plus 12x plus 4c. Log rules, I can divide this, so it's equivalent to ln absolute value y minus 2 over y plus 2 equals 4x squared plus 12x plus 4c. E to the power of both sides, y minus 2 over y plus 2 equals e to the power, let's say exponent 4x squared plus 12x plus 4c. And now I can just, well, I have to divide this. What would happen if I divided that? I would get something.
I think there is some cases where we can't like solve for y.
No, you can't.
That's true.
Multiply
can't
by the denominator of the y, and then
I was just seeing if there's some better way to do it, but yeah, no, that is the only way, I think. Well, not the only way. I think you could have divided, but I don't want to do anything too confusing right now.
Just c by.
What'd you say?
Can't you write 4c as a c by itself? Because you just multiplying a constant by 4s.
Yeah. Pretty much. You could. Just thinking, I don't want it to be more confusing. I guess it kind of already is more confusing by putting a 4 there. I don't want it to run into any complications. I know, I understand it could just be that, but I'll explain in 1 second why I'm writing it as a 4c. Let me just finish this question. So 4x squared plus 12x plus 4c equals 2 plus 2 exponential 4x squared plus 12x plus 4c. And then we just have this. So y equals 2 plus 2 exponential 4x squared plus 12x plus 4c over 1 minus exponential 4x squared plus 12x plus 4c. Okay, so I rearranged it for y here, and that's probably right. 2...
You couldn't factor out the 2 because you wouldn't cancel because it's a positive, correct?
I can factor out the 2, but why would I? Oh.
No, because I'm saying if you factor out the 2, you would not be able to cancel it.
I would not be able to cancel. I would not be able to cancel, no. So now we have to apply... Yeah, sorry, go for it.
I'm saying just leave it like that. I guess that's all you can do.
Yeah, that's right. So now we have to apply y equals 0 equals y of 0 equals negative 3. So what you could do is you could plug into this. Actually, it wouldn't be too bad because we're doing y, specifically because we're doing y of 0. You could plug into this, you know, wherever you see a y, plug in negative 3, and wherever you see an x, plug in 0, and then just solve for c. But there is an easier way, right? So we can go to an earlier version of the equation where it's less complicated and we can just solve for c there. And that's why I don't rewrite this as a new variable, because that lets you be able to go back to any of these equations, any one you want here, that's already integrated, so I guess any of these, and use that to solve for c. That is the same c as right here. If I were to just say 4c equals c, That's true, it's a constant, but it's not the same c as all of these, right? It's a different c. So we would not be able to go back here and use any of these equations. If you replace it, you can only use the last equation. Unless you can like really think about it as you're going through here and not make any mistakes and still use it, which you can do. But that's why I leave it as 4c, because then I can look back here, and in fact, I'll use this one right here. So what I said was that y of 0 equals -3. So this tells me that it's going to be ln absolute value -3 minus 2 over -3 plus 2. That is a positive number. Good. Equals 4c. Right? And so just divide this by 4, and we have what c is. Let's just plug that into my calculator and see what it is. Ln
of 5 or something.
Ln of 5 over 4.
Ln of 5
over 4.
Over 4. Ln of 5. Yeah. That's 5 there. Oh, okay, yeah. How's that 5? Oh, that's a -1. Yeah. Ln of 5
over 4.
Okay, well, I can't simplify that in any way. That's just ln 5 over 4. Yeah, ln 5 over 4. So c equals ln 5 over 4. And so now I can go to this equation and plug that in, right? That's why I save it as a c. So plus 2 exponential, and actually I'll write it as an e to the now. So 4x squared plus 12x plus 4 times c. C is ln 5 over 4. So this is just plus ln 5 over 1 minus exponential, or I'll say e to the 4x squared plus 12x plus, again, just ln 5, because it's 4 ln 5, but there's a thing there. Remember, adding in the exponent is the same thing as multiplying outside the exponent. So I'm multiplying by e to the ln 5, which is just 5. So I can move the 5 to the front here. Right? And then here I can do a very similar thing. So this is just going to be e to the ln 5, which is just 5. So this makes this 10. And we get a different number than what is in the solution here. So different coefficients. So let's see what's up, but probably just some stupid mistake somewhere.
So how did you find out c? Did you just plug it in back into like the original? Or
any equation here I can use. I plugged this in. That it gave this to us in the question. Y of 0 equals 3. So that means wherever you see y, you put a -3, and wherever you see an x, you put a 0.
Okay.
Right, and then just solve for c, which is I got this here.
Yeah, and then just solve for
Okay, I am off by some constant, so let's see what's up here. 1 plus. Well, not even off by like a multiple of a constant. This is supposed to be a 6, and this is supposed to be a 3. Somehow something happened. I mean, I'm multiplying by 5 definitely, right? C2 is. Let's see what I got. C2. 2.
Did we do the partial fractions wrong? Is that possible?
That's possible. Let me just see here. Exponential 4c. This is going to be 8. Yeah, we get 8c.
At the beginning, when you did, how'd you get 4x squared? Isn't it 2 over 3 times 4?
Where did I get 4x squared? Where?
So you have
higher up or no?
Certain point. Oh, I guess it's just x squared plus 3x. Oh no, that's fine.
Yeah.
Let's see. Okay.
Adam, you should explain the whole question so like you find a mistake.
Yeah, I will do that. So let's start from the beginning here. Y prime equals 2x plus 3, y squared minus 4. That's a separable differential equation. It's an initial value problem because they give us an initial value. So first things first. Question?
When you differentiate 2x, or when you integrate 2x, doesn't it become, no? Oh, forget it. I think you got it.
You got it? Okay. So we have f of x and g of y. So 1 over g of y dy equals f of x integral of f of x dx, which is correct so far. That's going to be x squared over 2 times 2, which is x squared, plus 3x plus c, which is not there. Y plus 2, y minus 2. I'm going to do some partial fractions here. Y plus 2, y minus 2. a over y plus 2 plus b over y minus 2 is 1 equals a y minus 2 b y plus 2. Solve by putting in y equals 2. That means we have 1 equals b4 or 4b, which is b is 1.
Wait, why did you put y equals to 2? Like, where did you get that from?
I'm just choosing that. I'm choosing y equals 2. Or picking that.
Or why are you picking that? Like, how can you pick numbers? Because once you have to expand, you have to
Pencil kind of solve for b.
Yeah, it helps to solve because if I pick y equals 2, right, then I know that this is a 2 here and that's a 0, so this whole term goes away. And then I can just solve for b.
I didn't pick big numbers. I thought you would have to like expand it into ay minus 2a and then have to do like algebra.
You can, but you can also do it like this. You can just pick some value for y. Y is any number, right? Y can be any number. So if you just
it was like the linear algebra method, and it was like this method.
Yeah, this is the second method. This is the other method that you do it like this, right?
Right. Yeah, I get it now. Okay, thank you.
Good. So pick y equals 2, I get b equals a quarter. Pick y equals negative 2. This is gone, so this is going to be 1 minus negative 4a. 1 equals negative 4a, so a is negative a quarter. That's fine. So I can then integrate negative a quarter over y plus 2 plus 1 quarter over y minus 2. Seems right to me. X squared plus 3 plus c. So negative a quarter ln absolute value y plus 2 plus 1 quarter ln y minus 2. So I just rewrite that again. Everything's fine here. X squared plus c. Then I have multiply both sides by 4. So I get 4x squared plus 12x plus 4 here. And then this is this one. I switched positions here, but it's still right. Then here I do, that is the ln rule, right? That minus that is that over that. Yeah, I think that's right. Then I have, I did just get rid of the absolute value for no particular reason, so didn't, but same reason as before. Like exponential is always positive, so we can just get rid of it. So 4x squared plus 12x plus 4c, that's fine. E to the power of both sides is fine. E to the 4c is fine. Multiply both sides by y plus 2. That's going to be y minus y times the exponential function equals 2 plus 2 times the exponential function, which is fine. And then finally, y equals 1 minus this exponential function. Yeah, I can't tell what's wrong.
I think our textbook is just not that great.
Just to be clear,
they didn't do well in Calc 2. They only passed with like, well, they might not have passed. Maybe that's why.
That's why, yeah. Yeah. Okay, yeah. Joshua was saying something?
No, I was just saying, when we included C, did we include did we do ln 5 over 4, or did we just do ln 5?
It was ln 5 over 4 but it's just being multiplied by 4, so it's just ln 5.
Okay, that makes sense now.
I don't know what to tell you. Let's take a look. Let's just.
I say we give the authority to say that we're right.
Let's just plug it into. Yeah.
What does the answer say? Can you copy the answer into the one?
Yeah, the only difference is I'll paste it on here.
Yeah, usually a good rule of like usually when you try to explain the question, you find your mistake, but then when you explain it, still didn't find a mistake. So it's.
There's also the difference in signs in the numerator.
Oh, that's true.
Yeah.
Okay, I'm just gonna plug this in quickly to Wolfram. Solve y prime equals 2x plus.
I tried to pay attention to I paid attention to the question too, like nothing seemed wrong either. So like.
Yeah. Where y of 0 equals -3.
Just a quick question.
Yeah.
So we don't have to solve for y unless the question is asking us to solve for y, right? We can keep.
Well, no, you do have to solve for y because then that's the solution. If it asks for the solution, then you do have to solve for y.
Oh, I thought it's like if only it's specified in the question, we have to solve for y.
No, if it asks you for like what's the solution to the differential equation, it's some function y equals f of x. So y equals f of x equals this.
Oh, I see. So yeah.
At the end, you need a function.
Wolfram says what we said. Wolfram says this.
Yay!
Wolfram says
Yeah,
that's it.
we are both.
Yeah.
Screw you, textbook. I didn't like you anyways.
There you go. Very good. Wolfram
There's a glitch in the system.
There it is.
I think the textbook's answers are by college students, so
Yeah.
they just put students to do the answers.
Yeah.
And they messed up everything, and
So
there's
it's
no
kids,
work. Yeah, I don't know.
kids our age who don't know math.
Not our age, like third and fourth
That's very
years.
no, that's very
Okay, so let's try.
Okay.
Let's try. See, we have another kind of differential equation that we can move on to. So this is the. This was just separable differential equations, and there are word problems for all these things, but I don't know. I don't feel like they're going to give us a word problem. They didn't give us a word problem on the mini test. I think they would only give us a numerical problem.
They're not allowed to.
They're not allowed to.
No, because not every professor covered them.
Okay, then yeah. I just didn't. Yeah. Makes sense to me.
Because not everyone. But that's what happened last time on the very first calc test. So
Yeah, that's true. We talked about this.
I mean, straight from CTW, he said if you get a word problem on any test, I didn't cover that, so just tell me and like ask for a remark. And,
yeah.
You shouldn't be graded on that.
Yes, but I
So-
guess so. But like,
Yeah.
no, I was just saying that semester, didn't we get like worded questions in the end? Like, I think there was one read question. Wasn't it a worded question?
In the textbook, we got textbook questions that were word questions, but not on the test.
Oh,
Not on the
okay.
test or anything. Yeah. Okay, so let's move on here to linear differential equations. So this is 4.5. We just start with what the definition of a linear differential equation is, and it's this. So it's y prime plus some function of x times y equals some function of x, right? So if you want to solve this, I'll go through the steps described here quickly. So if you want to solve this, y prime plus p of x y equals q of x. Well, okay, so the idea that we want to do here is we want to make this to be integrable, right? If we could integrate that, that would be nice to be able to do. One thing we know how to integrate is if we had y prime, well, let's say like f y prime plus f prime y. We want to integrate this, right? This is a product rule. So this would be f y, right? That's what this would be, because this is the derivative. This right here is just the derivative d by dx of fy, and the integral and the derivative cancel out. So if we could make this into some form of fy prime plus f prime y, that would be very nice to be able to do. Well, we already have y prime and y here. We just have to make somehow 1 and p of x to be our f and f prime. So when you take the derivative of this thing, right? If I put anything here like 2, we have to be able to get a 2 here, right? The derivative of it has to be here. So the derivative of it, when we get a function outside of the derivative. That's kind of like an exponential function, because the exponential function, if you have e to the p of x, then you're going to have p of x prime, right, times e to the p of x. So we want this thing to be the derivative. So what we do is we define this thing called a integrating factor. Integrating factor as an idea is used all the time in differential equations. The specific integrating factor for linear differential equations will always be e to the integral p of x dx. Because look what happens now. If I multiply both sides by this integrating factor, I get e to the integral p of x dx y prime plus e to the integral p of x dx p of x y equals e to the integral p of x dx q of x. And now look at this. It might not be instantly apparent, but this is just the product rule, right? If I were to integrate this, integrate that side, so if I integrate both sides now, right, then that's just going to turn into e to the integral p of x dx y prime dx. Sorry, I'm writing huge for some reason. So notice for a second, right? That's the derivative of this is this. So it's going to be the first one times the derivative of the second one plus the derivative of the first one times the second one. And this is equal to the integral of e to the integral p of x dx q of x. Sorry, q of x dx. So the right side here is just nicely just this thing, e to the integral p of x dx y is equal to the integral of e to the integral p of x dx q of x dx. And finally, to rearrange for y, I just do 1 over e to the integral p of x dx. And there we go. We have a solution. Y equals something. Right? And that's described in a nicer handwriting here. So if you want to see the same thing, then it's in my notes here, of course. And you can rearrange for y. And now we have a solution to the linear differential equation, which means we have a solution. That's the answer.
So, like, on a real question, let's say we get a question, could we just directly go to like the last step, or we do?
Yes. You can go right to the formula. Just like here, I mean, there was only 2 steps in the separable differential equation, right? You go from this to this to this, right? But you can just jump right to this. I go from the question to that here, right? So in the same way, I can go from this directly to this, and that will work. That will be fine.
Okay, thank you.
No problem. So let's give it a try. So if I go here, let's see. No, that's not fine. That's not okay. What is this? Okay, that's fine. So let's say we have x, y prime plus 3y equals 4x squared minus 3x. Okay. So here we have a... So here we have a linear differential equation, right? It's not in standard form though, right? It's not quite in standard form. So standard form, remember, is y prime plus p of x y equals q of x. So it's not quite in that form yet. We just got to divide everything by x. So y prime plus 3 over x y equals 4x squared, well, 4x minus 3, right? 4x minus 3. Okay, now it's in the correct form. We're going to define an integrating factor. Our integrating factor, I of x, is the integral of e to the integral of p of x dx. P of x is 3 over x dx. So this is going to be e to the 3 ln x, ln absolute value x, plus c. So we can't forget the plus c. There is a plus c up there now. Oh, never mind. We can't forget the plus c for now. This plus c doesn't matter, I guess, because you're still gonna have a plus c because of this integral. So just at that point, include the c. Here you can just say c equals 0. Okay. So this is going to be e cubed x. What? How is that not?
No, isn't it going to be x cubed? Don't you move the 3 up into the x?
Yes. Sorry. I just yeah, that's right. It's just going to be x cubed. Yeah, x cubed is right. Because this 3 goes up here, and now that's more apparently x cubed. Okay, so now we have that. I'm going to multiply both sides by this integrating factor, right? Or, alternatively, I could just jump right to the solution here. So y equals 1 over the integrating factor, x cubed, times the integral of the integrating factor times q of x, which was 4x minus 3 dx. Right? And now I can go here, well, this is 1 over x cubed times the integral of this, well, this is going to be 4x to the 4 minus 3x cubed dx. And now I go and do that. So x cubed, this is going to be 4 over 5 x to the 5 minus 3 over 4 x to the 4 plus c now. And we don't have any initial values. Yeah, we don't have any initial values, so we just want the general solution. So this is essentially the general solution. I mean, I don't even have to multiply the x cubed in. No, I guess I will, but you don't actually have to. So this is going to be 4 over 5x squared minus 3 over 4x plus c over x cubed. And there we go. That is the general solution. The problem is complete. Okay, I will do, let's see if there's another one. Oh, there's even like an application in electric circuits here, interestingly. Wow.
I mean, if you...
we did that in class. That's how we did RC transients. It was solving a differential equation.
That's true. Yeah. I'm just surprised to see it in the textbook. Yeah.
You can use the one from the study hall if you're looking for one.
I have one here. I'll do this other one from the textbook. But if people want to see another one, then yeah, I can do that one too. Yeah. But thank you. Y prime plus 3y equals 2x minus 1. So that's already in standard form. That's good. Remember, standard form is y prime plus p of xy equals q of x. And we have an initial condition this time. Y of 0 equals 3. So let's give it a try. I can jump right to the solution, honestly. So y equals 1 over e to the integral 3 dx times the integral of e to the integral 3 dx times 2x minus 1 dx. Just using this formula right here. Right. So, well, what's this? Y equals 1 over integral 3 is 3x. So e to the 3x, that's fine, times the integral of e to the 3x times 2x minus 1 dx. So, now I can do, I think I just have to do this and then do partial fraction. I mean, and then do, forget the name. Not partial fractions. Integration by parts. So this is going to be e to the negative 3x times the integral of 2x e to the 3x dx minus the integral of e to the 3x dx. Yep, it's just this is in a bracket like that. Okay. Y equals e to the negative 3x times, okay, well, I can move the 2 out, right? So times 2 times this integral. Now, we'll deal with this integral in a second. So this is going to be x e to the 3x dx. And then this is just going to be, well, what's the integral of e to the 3x? Well, okay, what's the integral of e to the x? That's e to the x. Is it e to the 3x? The derivative of this is 3e to the 3x. So if I multiply both sides by 1/3, both things by 1/3, I get that. So the antiderivative is 1/3 e to the 3x. It's going to be minus 1/3 e to the 3x. Close that. And now to integrate this, I'm going to have to do integration by parts. So I'm going to say u equals x, dv equals e to the 3x, du equals dx, v equals 1/3 e to the 3x dx. So now this fraction is equivalently, I'm going to have to write it all out now, minus 3x, 2 times uv, so x e to the 3x over 3 minus the integral of v du. So 1/3 integral of e to the 3x dx. Close bracket, close bracket. No, not close bracket once, minus 1/3 e to the 3x. Close bracket.
The
Okay.
dx is on the dv, right? Instead of the v? For the integration.
Yeah, you're right. This is supposed to be dx, yeah. Yeah, that's right. So then now I just rearrange. I mean, I just do the integration. So it's going to be I'll multiply the 2 in. I'll multiply the 2 into here. That 2 is only multiplied there. Yeah, so it's going to be times 2/3 x e to the 3x minus 2/3 times 1/3 e to the 3x minus 1/3 e to the 3x plus c, finally. So now I'll multiply e to the negative 3x in. So look what's going to happen. I mean, I'm going to get 2/3 x minus 2/9 minus 1/3 plus c over e cubed, e to the 3x. Right, so a lot there cancels because I have 3x and negative 3x I'm multiplying in. So y equals 2/3 x minus, this is going to be 3/9, so negative 5/9, but I'll put that at the end actually, plus c over e to the 3x minus 5/9. Okay, we're pretty much at the solution. I just have to figure out what c is. So I go back to my initial condition. Y of 0 equals 3. And so this is the simplest form of it, so I'll just do it here. Y of 0 equals 3. So that means that 3 equals 0 plus c over e to the 0 is 1 minus 5 over 9. So 3 plus 5 over 9 equals c. 3 plus 5 over 9 is 32 over 9. Yep, c equals 32 over 9. And so finally here, I can just put y equals 2/3 x plus 32 over 9. No, 32 over 9 e to the 3x minus 5/9. And that is our solution to the differential equation. Yep.
What if there's, if you scroll up a bit,
yep.
We're a bit more. What if it's like a negative? You know, where you have to integrate the left side, which has the dy dx and the
y, this left side here.
Yeah. I don't know why my brain froze
okay.
for a second. Yeah. So what if it's like, because I sent you a question where this ends up being negative on this side, where the y prime minus the 3 of, gosh.
Yeah, y prime minus 3y.
Yeah, it's like 3y. Negative, yeah.
Where's the negative though? Negative 3.
It's gonna be between them. So it's y prime minus 3 of y, which is like the second. So it's, usually it's just
so
f of y plus g of y.
So you mean this, just like there's a negative here? Is that what you're saying? Or
yeah.
Well, it's just like it's just your p of x would be negative 3 in that case, right? Your p of x would be negative 3, and then it'd be integral negative 3 here. That's the only difference. Does that make sense? Is that what you're asking?
Yeah, I think so. Because I sent you a question that has it.
Oh yeah. So it's I see what you sent. Okay, we'll do that too.
It's gonna eventually.
I have another question that we're gonna do too. Yeah, I'm gonna do the questions that people sent me. Maybe after our break, then I'll do the questions that people sent. First, I want to just get through this, and then after we're done, how about this? I'm gonna do the mini test now on the differential equations, and then afterwards we will do the questions that people sent. So, are we good to go to the mini test now?
Also, one more thing. You said something earlier, like at the beginning with p of. Like you had p of x and p and you had the integrals with it a bit more. I think it was at the beginning of here? Yeah, you were explaining something here that I didn't really get what you were trying to say with the.
Yeah, essentially, I'm just deriving this formula, right here. That's what I was doing, deriving this formula. Right from this. How do we get from this to our formula at the bottom there, right? And so these are all the steps. If you, it's nice written nicely in my notes. So if you want to look there, they're
there. Oh, do you think?
Okay. So let's try the mini test now. Mini test is going to be So my mini test was 1 minus cos x. Y prime equals sine x squared minus y. Okay, it's with an initial condition of y to the negative pi over 2 equals 0. Okay, so there's a few ways to look at this. I think I did it the linear differential equation route, but sometimes it's a little ambiguous as to whether it's a linear differential equation or a separable differential equation. But here we can rearrange this in just a few steps to be a linear differential equation. So that's about how I do it. So I get 1 minus cos 1 minus cosine x. Come on, don't mess up on me now. What's happening? Look, it's doing something weird. Let me restart OneNote and see if that fixes it.
It's infinite again.
Yeah, let's seem to fix it. Okay, hopefully it doesn't start. It's done that before to me while I'm doing ELE, and don't know why it does that sometimes. Okay, let me rewrite this. 1 minus cosine of x y prime equals, sorry, well, not equals. No, you know what? I will do equals. So equals sine of x squared minus y sine of x. Okay, so then now I'll just rearrange to get it in the proper form. So y prime, no, I'll write properly. 1 minus cosine x y prime plus y, or plus sine x y equals sine x squared. Now I'm going to divide everything by 1 minus cos x, so y prime plus sine, sorry, that should be negative, shouldn't it? That should be negative. No, it shouldn't be negative, sorry, it's negative here, and then it'll be positive now. Sine x over 1 minus cos x, y equals sine x squared. We're in standard form now. I have to identify the integrating factor. Right? Or I could just go right to the equation. Yeah?
We have to divide sine x squared by
1 minus cos x. That is right. Thank you. Now we're in standard form. And so I can go right to the actual solution. So y equals 1 over, I'm going to give myself lots of space here. So 1 over e to the integral sine x over 1 minus cos x dx times the integral of e to the integral sine of x over 1 minus cos x dx times sine of x squared over 1 minus cos x dx. Now we just got to figure out what this is, so let's get going. Well, we have to integrate. First step is to integrate sine x over 1 minus cos x dx. So how will we do this? We can say 1 minus cos x isn't much.
Can we use u du? We can use substitution.
Oh yeah, we can just do a u substitution. You're right. So u equals, thank you, u equals cos x, du equals negative sine x dx. So it's going to be negative the integral of 1 over 1 minus u du.
Excuse me.
Yeah.
Couldn't we do 1 minus cos x? So then that gets rid of the negative.
It would be the same thing. Yeah, you're right. You're right.
It will get rid of the negative sign. It will get rid of the negative, and it will get rid of the negative side up, like in the front.
Would it? No, it wouldn't. It would still have negative in the front.
It will be 1 minus cos sine, so it will be negative times negative sine. It will be just sine.
Oh yeah, yeah, that's true actually. Yeah, but I'm gonna get the same answer here, so it's gonna be ln absolute value 1 minus cos x as my integral there. Yep, ln absolute value 1 minus cos x, and so that's our integrating factor. So now let's do that. So it's gonna be y equals 1 over.
Wait,
yeah.
Don't you have to re-include the negative?
Which negative?
It's a negative sign out the front. Like, didn't you take a negative sign out because of the negative sign?
Yeah, but then what's the integral of
Or
this?
the
What's the integral of this right here? It's
Oh.
it's negative ln absolute
Negative
value
ln,
1 minus
yeah.
u. So the
Okay.
negative and the negative cancel.
My bad.
So integrating factor, ln absolute value 1 minus cos x times.
Isn't it e ln? I'm sorry, I know you're writing, but isn't
yeah,
it
you're
e
right.
ln 1 minus cos x? So it's just 1 minus cos x.
You're right. You're right. Thank you. Thank you. Yeah, it's e to that, not just that. It's e to that. Exactly. Sine x, x squared, 1 minus cos x dx. Is that what I had? Yep. So now this simplifies a little bit. It's just going to be 1 over absolute value 1 minus cos x. Does the absolute value need to stay? Cos x goes from 1 to negative 1. 1 minus 1 is 0. 1 minus negative 1 is 2. So I think 1 minus cos x stays above cos
I think
x.
you can ignore it.
Yeah,
You can ignore it.
we can ignore it. The reason is because it's always positive. So there you go. So it's just going to be 1 minus cos x integral 1 minus cos x 1 minus cos x sine x x squared dx. So those cancel, and we just say y equals 1 over 1 minus cos x, the integral of x squared sine x dx. And this is just a integration by parts question. So let's integrate this by parts. I'm going to choose u equals x squared du, well, dv equals sine x dx, du equals 2x dx, and v equals negative cos x, negative cos x. So I can write this as y equals 1 over 1 minus cos x times uv, negative x squared cos x, minus the integral of v du. So plus v is, that du is 2x cos x dx. And I'm going to do another integration by parts. U equals x, dv equals cos x, dx, du equals dx, v equals sine x. So this is going to be y equals 1 over 1 minus cos x times...
Negative. Sorry.
Negative?
I think it's negative sine x.
No, the derivative of sine is cos.
Oh.
That way, right? Yeah, don't worry, don't worry. I'm going to multiply this 1 over 1 minus cos x in, so it's actually going to be negative x squared cos x plus 2 over 1 minus cos x times, nope, yeah, times v du x sine x minus the integral, sorry, uv, which is x sine x, minus the integral of v du, sine x dx. Okay, y equals negative. I'm gonna take the negative out of the top there and put it on the bottom. So it's gonna be cos x minus 1 plus 2 over 1 minus cos x. Oh no, I'm gonna multiply. Sorry, I'm gonna multiply that in. So then I'm gonna get a 2x sine x minus 2 over 1 minus cos x times the integral of sine x. The integral of sine x is negative cos. So plus cos x, times cos, 2 cos x up there, plus c. Okay, there we go. Now we have to take into account the initial value. Let me just make sure this is what I got before, and then we will be able to do that.
Would we have to divide c by 1 minus cos x as well?
Your first fraction.
Yes, I guess so.
Denominator is kind of open. It's supposed to be 1 minus cos x, not cos x minus 1.
Yeah, but I took the negative from here. I took the negative from here.
Oh.
And put it on the bottom.
Okay.
So it's the same thing.
Okay.
I guess actually that overcomplicates things because I can't factor out a 1 minus cos x now. So let's not do that.
That's what I was thinking.
Yeah. And then yeah, I guess I do multiply this by a 2 over 1 minus cos x times c, and then there we go. that part doesn't particularly matter if you don't want to use earlier equations. And in this case, actually, we don't want to use earlier equations at all. So actually, totally fine to not do that. So I could right now. No, could I right now say that actually? No, I couldn't say that because there's an x here. So I do have to do this. I have to do that. Yeah. Okay, now I'm going to, this was my initial value problem. Yeah. My initial value in particular was negative pi over 2. So the way I did this, I have to do that. Okay. 1 minus cos x y. Just multiply. So right now, like, this is a solution. We have to solve for c now. We're applying our y equals negative pi over 2. Y of negative pi over 2 equals 3. Or equals 0. What was it? Y of... I went too far, didn't I? No, I didn't. There. Y of negative pi over 2 equals 0. So I'm just going to multiply both sides by 1 minus cos x so that it's a little simpler. Plus 2x sine x plus 2 cos x plus 2c. Yeah, I only had c there. That's strange. Why did I only have c there? Oh, did I just call 2c c? I think I just called 2c c. And that's fine to do. That's okay to do. Okay, so now we want to plug in the actual value. So it's going to be 1 minus... Now, I'm not going to write it the whole time. So it's going to be just wherever you see x, put negative pi over 2. Wherever you see y, put 0. So it's going to be 0 equals negative x squared. So this is going to be negative pi squared over 2 times cosine of pi over 2, which is 0.
Isn't it positive? Because you have a negative, you plug in x equals negative pi over 2?
X equals negative pi over 2, but there's still a negative sign on the outside there.
The cos function symmetrical. A negative angle doesn't change your answer.
But he's asking about this negative sign here. This negative sign, like, right.
Oh,
there on that side, yeah. But actually, this is times 0, so that's fine. Plus, this is going to be, well, minus pi. Sine pi over 2 is 1, so minus pi, plus 2 times 0 plus 2c. So this is 0. So there we go. C equals pi over 2. That's not the answer I got before. Oh no, C, sorry. C equals pi over 2. Yeah, that is the answer I got before. C equals pi over 2. It's just confusion with the 2 here, but just always leave the 2. There will not be confusion if you just always leave the 2. Or always leave C as the variable, put all the things on it. So finally, I can write the answer as negative x squared cosine x over 1 minus cos x plus 2 sine x over 1 minus cos x plus 2, sorry, there's an x here, 2x sine x plus 2 cos x over 1 minus cos x plus 2 over 1 minus cos x times pi over 2. So that goes away, and you just put, so c is pi over 2, right? So it's just pi. That is the answer. There we go.
Isn't sine negative pi over 2 negative 1? Or am I wrong?
Yeah.
I'm getting negative 1 on my calculator.
You're right. So, yeah, sine negative pi over 2 is negative 1. So then this would be, where did I go wrong here? Then this is 2, 0, 2 times, this is negative pi. Oh no, I did account for that. No, I did not account for that. This would be positive.
It's negative pi times negative 1, so it's just positive pi. So then it's just, c is negative pi over 2, so then when you write your final, it's just going to be minus at the end. And these,
yeah.
like your y equation.
That now doesn't match my answer though. So let me check. Let me just type this into Wolfram and see what the actual answer is.
It's funny if you made a mistake and even the people who were marking it didn't see it.
That would be nice.
That happened for one of my mini tests. I forgot a negative, and then I still got the mark for it. So.
Yeah.
They probably didn't see that.
I got saved.
Yeah.
You know, a negative sign is just an arbitrary concept.
Yeah. Hopefully, I wish.
So let's see what the answer is.
If you go to Bitbolide, there should be the answer there as well.
That's true. That probably is better. Wolfram gives you answers in like simplified terms, and it's weird. Oh, what? This was mini test. Mini test what?
4.
4?
4.
Mini test. Mini test 4. Yeah, it is supposed to be minus pi. Oh, what? Yeah. Yeah. So I technically didn't. They even circled my mistake. This is my actual mini test when I did it. They circled my mistake, but you see here I actually solved for c equals negative pi, but then when I plugged it in, I just used pi for some reason. So they still gave me the mark because I found c equals negative pi. It's just that when I plugged it in, for some reason, I used pi. I don't know why I did that, but just not paying attention, I guess. So yeah, so this is for sure negative because this is positive, so this is negative. And there we go.
So on the mini test, you said it was negative.
The answer is negative. The answer is with a negative sign.
No, but you said negative pi. This is negative pi over 2.
Yeah, I was saying the factor of 2. What happens to that?
Well, that's just because I did it slightly differently. I technically said d equals 2c, and I solved for d.
Oh.
I solved for d, which was negative pi.
Okay.
Right. But that's just a technicality. Like, it doesn't really matter. Again, I just say leave it as a variable and solve for c, and plug in c, with everything around it. Everything is being multiplied and added to and divided by.
Let's go to the integral part of the question again. I have a question right here. No. Right down. A bit more. Like this slide right here. That's not fully. Yeah, right here. When you had the. Was it? Oh, I'm sorry. Was the 2 over. Actually, it was multiplied because it's integral of sign. You got the negative sign, but it was multiplied by the negative sign outside, and then you multiplied it by the 2 over 1 over cosine x, right?
Mm-hmm.
Okay, that's all.
That's good.
All right, thanks.
Good. Yeah. Okay, let's take a little bit of a break. Let's take maybe like really a short break because I am going to take a break at 8 o'clock again because I always have to take a break at 8 o'clock. So let's just take a break until 7:25. Let's say that, and then we'll break again at 8. So let's take a short break. I'm just going to get some water. I mean, I've been drinking water this whole time.
What chapter do you plan to stop at? Like, are we stopping at chapter 6 or chapter 5?
I think we'll do some of chapter 5. I definitely want to do like I said at the beginning, I definitely want to do the comparison tests again, or the limit comparison and comparison test again. So maybe up to that, and then we'll start doing like practice midterms and stuff like that, or whatever.
All right, sounds good.
Okay, I think that's the idea.
So we're done chapter 4.
We are done chapter 4. Yeah.
Okay.
We're done chapter 4. I do have 2 questions that were sent to me. I'm going to do that right after the break. And so we'll do that then. Okay, so let's take a break until 7:25, and then we will work from there. Oops. Let me just edit the text though. For some reason I can't easily. There we go. What did I say? 7:25. And yeah, we're still doing a break at 8 o'clock, so don't worry if you need to take a break at 8 o'clock. There you go. Okay, so back soon.
Only 2 more tests to go.
Is it bad that we have the worst tests for last? Would you prefer to have like the math and the ELE at the start of the exam period?
Yeah.
I would say yeah, yes.
Because if I had physics right now, I'd be like, I wouldn't be like so over the top with it.
It didn't give us any days between it. Like it's like math and right after it on Tuesday.
Yep.
It didn't give us this gap.
I mean, at least the math is like, I think it's what, between 9 a.m. and 9 p.m. tomorrow. So,
Yeah, 3 hours long, 6
so
questions.
I don't have to wake up at 9 o'clock in the morning.
Just do it really early and then have like the rest of the day to like focus on ELE.
That's what I'm gonna do.
I'm gonna do it. I'm gonna do it at 9. But right away, I need to study for my
9.
For my other for my next.
Yeah, I don't know if I'll do it at 9,
study.
but I'll do it.
Do it, you won't.
Okay, guys, I am back. Hello.
Break over.
So yeah, let's get back into it. I'm gonna do the 2 questions that were sent to me. So let's take a look. I will do this. I'll do yeah.
Question: are you planning to do anything tomorrow, or just because it's like from 9 to 9 you can't do anything?
I can't do anything tomorrow. No, I can't do anything tomorrow.
Yeah, I see.
Yeah, because I'd have to do it before 9 o'clock, right? I can't do it before 9 o'clock. So.
It's 60.
So okay, Joshua sent me this question. So let's take a look at it. It is just to show a differential equation given as y prime that use the general solution of the differential equation is show that the general solution is that. So okay, well we can show that this is true by so if this is true, if this is actually a solution to this differential equation, y prime cos x equals y sine x plus sine 2x. If I plug y into this, if I plug y equals 1/2 secant x minus cos x plus c secant x into this, it should be true. The left side should equal the right side. So let's give it a try. I'm gonna have to know what the derivative of secant is. I don't quite know what the derivative of secant is. Derivative of secant 1 over
it's secant x tan x.
Secant x tan x? Okay. Thank you. So I'll do that here. It's going to be 1/2 secant x tan x. That's what the derivative of secant is? Oh, yeah. Yeah, I remember now. Minus derivative of cos x is negative sine, so plus sine x plus c times secant x tan x times cos x. This should be equal to 1/2 secant x minus cos x plus c secant x times sine x plus sine 2x. Okay, so let's multiply this in. So it's 1/2 secant x tan x cos x plus sine x cos x plus c secant x tan x cos x equals 1/2 secant x sine x minus cos x sine x plus c secant x sine x plus sine 2x. Okay. Now, I'll turn everything into sines and coses, pretty much, and show that left side equals right side. So secant, so it's going to be 1/2. Secant is 1 over cos. Tangent is sine over cos. Cos x times cos x plus sine x plus cos x plus c times 1 over cos x times tan x, which is sine x over cos x times cos x equals 1/2 1 over cos x sine x minus cos x sine x plus c 1 over cos x sine x plus sine 2x. Okay, well, let's keep simplifying. So this is going to be 1/2 sine x over cos x plus sine x. That should be times, not plus there. Times sine x cos x plus c times sine x over cos x equals 1/2 sine x over cos x minus sine x cos x plus c times sine x over cos x plus sine 2x. Okay, we're almost there. So what matches? That matches with that. That matches with that. So essentially now, although I can't really subtract both sides. No, can I subtract both sides? Yeah, I can subtract from both sides.
Yeah, as long as you do something to both sides, you can do it. Like, it doesn't matter what you're doing.
When you're showing left side equals right side, you can't always just subtract. Like, you're trying to prove something. But why wouldn't you be able to in this case? That doesn't quite make sense. Yeah, I mean, or you can just think of it like this. We now need to show that this equals this plus this, right? So we need to show that sine x cos x. Oh yeah. We can do this. Sine x cos x plus sine x sine 2x, right? And well, let's just see some identity. I don't know. Sine.
I know. Can't you add sine x cos x to both sides and then use identity or something like that to cancel this out?
I don't think you're allowed to do that, to add to both sides if you're showing something's equal to something else. Yeah.
This is a proof. You have to do left-hand side.
Yeah, you just have to keep left-hand side and right-hand side separate. I can't just add both sides here, sine x. I'm trying to show that left side equals right side, right? So.
Okay, so I guess just do sine 2x, whatever that is. 1 plus.
Yeah, sine 2x is 2 sine x cos x. That's
yeah, exactly. So sine x cos x equals negative sine x cos x plus 2 sine x cos x. So finally, sine x cos x equals sine x cos x. Check. Left-hand
Can you
side.
go back up to the top after you're done? I was just
here.
Yeah. Okay. So the tan. Okay. Thank you.
Good. Okay. No problem. So yeah, there we go. They are equal. That's fine. We did it. So we showed it's equal by doing that.
There was a part B that just says y of 0 equals 0. Show that, and that was about it.
Y of 0 equals 0?
Yeah.
Show that y of 0 equals 0? Or show...
It says, hence otherwise, solve for the initial value problem, y prime cosine x equal y sine x plus sine 2x.
Oh, I see. Yeah. Well, you could just take this equation, take the solution, and whatever, what was it? Sorry, it was y of something equals something?
Y of 0 equals 0.
Y of 0 equals 0. So you can just say 0 equals 1/2 secant 0 minus cosine 0 plus secant 0. I don't know what secant. Secant 0 is 1 over cosine, so 1 over 1. So secant 0 is 1. Cosine 0 is 1. So just solve for c here. It's just going to be 1 minus 1/2 equals c. C equals 1/2.
Yeah.
And there we go. Just from the solution. You already have the solution, so you don't have to solve for the solution. Okay, then that's that question. Then I have this question that was sent to me from my friend Yusuf. So, yes, there we go. Let's see. Did it move everything? It moved everything. There we go. Oh boy, what's happening?
Can you just click on it? Does it pop back up?
I'll just close OneNote and launch it again. Oh no,
Trippy.
OneNote fully crashed. Even the other window of OneNote crashed. Okay, Okay, well, I can't control Z now. Yep. So, okay, let me try to fix this. Move this here. What did I just cut off? I just cut off something. Oh, 1 minus cos x from there. Okay, I'll move this in a little bit. There you go. And then, because if I screw it up, then everything screws up in the whole thing. So 1 minus cos x there. Okay, there's that. Now we have this question. Okay, so it's a pretty complicated one. So let's get into it. This is a 3.2 question, really. So it's fine, though. So I'm going to forget about the bounds until we integrate, and then I will deal with the bounds. Unless something's discontinuous at this, but cosine of 0 is 1, and cosine is not 0 between 0 and pi, unless cosine of pi over 2, but pi over 2 is bigger than pi over 3. Okay, so that's fine. Yeah, that seems right to me. So there's nothing discontinuous here, nothing weird happening, so I'm just going to indefinite integrate this at first. So to deal with that, well, I can first of all separate this. That's probably the best thing to do is to separate this. So this is going to be the integral of sine cubed x over cos to the 4x.
Why are we doing an indefinite integral for this one?
Just because I don't want to. I mean, I can do a definite and then just leave. Really, the difference is just writing the bounds here. And that's
you're just doing this for like convenience. Oh, okay.
Yeah, I'm just not going to write it, and then at the end I'm going to evaluate the thing. Right, that's all it is. Plus, well, right away I'm going to replace sine 2x with 2 sine x cos x. But so it's cos x, so it's going to be cos to the 4x. Integral that. Well, you know what? I'll just leave the integral there. Dx. Okay, well, I'll split this up now. So it's going to be sine cubed x over cos squared x squared. That won't help me. Never mind. That might not help. Okay, so anyways, but this is going to be 2 times the integral of cos to the 4x sine x dx. I'm just going to do a u sub now. U equals cos x. Du equals negative sine x. So this is going to be the integral of sine cubed x over, I'm going to leave this as cos to the 4x because I don't know what I'm doing there yet. So minus 2 integral u to the 4 du. So this is going to be the integral of sine squared x over cos to the 4x minus 2u to the 5 over 5. And u was cos. So cos to the 5x over 5. Okay, that's that first bit done. Now, sine squared x over cos squared x. I can replace, what can I replace? I can say u equals
sine to the 3. That's gonna mess you up.
Oh, that is sine to the 3. Okay, then I can do this now. Okay, now it's not too hard. So thank you. Yes, I can replace sine squared, and I'm gonna do 1. Okay, I'll rewrite this nicer. So sine cubed. This is gonna be the integral of sine squared x sine x over cos to the 4x dx. Sorry, there should be a dx here. Minus 2, whatever, I'll just copy this and I'll just copy and paste it each time. Minus 2 that. So, not 2 of them. There. So now what I can do is I can say sine squared is 1 minus cos squared. So this is going to be the integral of 1 minus cos squared x sine x over cos to the 4x dx minus, well, I'll just copy and paste what I had before. And then now I can just say u equals cos x because du equals negative sine x. So it's going to be the integral of 1 minus u squared over, sorry, negative the integral of 1 minus u squared over u to the 4 du minus 2 cos to the 5x over 5, or 2 over 5 cos. I could have copy and pasted, whatever. Now this integral. It will be partial fractions? No, can't be partial fractions.
No, just split it into 2.
Yeah, just split it into 2. Yeah, thank you. So it's going to be the integral of 1 over u to the 4 plus the integral of u squared over u to the 4 du. And then paste what I have here. So then this one here is just u to the negative 4. U to the negative 4, which is just going to be to integrate that. It's going to be yeah.
When you took out the negative sign from the numerator just now, was it you took it out from in front of the u, but wouldn't that have a negative one over in front, a negative sign in front of the 1 now?
Yeah, you mean like 1 over
Yeah.
u to the 4?
Yeah,
Well,
did
then,
you just...
There's no negative here now. It's positive here, so it should be positive here.
It was initially positive, or was it initially negative? Because that's what I'm kind of confused of right now.
What do you mean initially? Like it's positive
Yeah.
here.
Okay.
So it's positive here.
Oh, no.
It has there's a negative sign in front of the integral. So when I split this, right, it's a negative minus negative u squared. So this turns into just plus u squared.
Yeah, I was kind of confused when the negative sign came in, so I was like...
Yeah. Oh, don't worry. Yeah, that's...
Yeah.
So then here, this is u to the negative 4. So I'm going to integrate this. So add 1 to the exponent, u to the negative 3, divide by the new exponent. Plus, this is just going to be 1 over u squared, right? Which is u to the negative 2. And so that's going to be add 1 to the exponent, u to the negative 1, divide by the new exponent is going to be this. So it's just going to be negative 1 over u. And then just paste the thing here. And now sub u back in. U was cos x. So it's going to be 1 over cos, well, I guess I could just call it secant cubed x over 3 minus 1 over cos x. So it's just secant x minus 2 cos to the 5x over 5. And that's my answer.
Just one quick thing.
Yeah.
If we go up, can't we just before you start doing that, here, can't we just say no, yeah, here is good. Can't we just say it's 1 over cos times sine cube over cos cube, which is tan cube, so we have secant times tan cube?
Yeah, you could do that, but why would that help you? Oh, because secant tan is the derivative of tan? Yeah, you could do that too, yeah. Secant tan is the derivative of secant, I mean? Yeah. Oh, no, but... Oh, yeah, that would work. Would that work? Hold on. Secant tan... No, that wouldn't...
We took it in the trigonometric integrals, I think it was, beginning.
Yeah, but then look what you're going to be left with here. Look what you're going to be left with. If you turn that into that, it's going to be tan cubed x times secant x, right? So what are you going to choose for your u sub?
No, I'm not going to do the u sub. I'm just going to do what we learned in the beginning.
Oh, okay. Yeah. Okay, and then deal with it like that. Yep, that works. Yeah, you can do it. Yeah, that works.
You got, for your answer, go down a bit. You got negative secant x. I got positive. How do we get negative? Because aren't we multiplying? We have like 1 minus u squared over u to the 4th. So we would break up, like you have a negative there, but then you did negative u to the negative 4 du plus. Oh, I guess it would be plus though.
Yeah.
Okay. Never mind.
It would be plus there. Yeah. Okay. Good. There you go. So Yusuf, is that the answer? If you're listening, is that? Oh, is Yusuf here? I can't tell. No, he's not here. Okay, I just left. But yeah, then Yusuf, if you're watching, then there you go. There's your answer. So there you go. That's the question from 3 point. Kind of a bunch of problems. I guess it's a 3 point. 3 point what problem? It's a 3.2 problem.
Yeah.
Oh wait, it's a definite integral.
Oh, yes. So integral from 0 to pi over 3. So we evaluate this now. Secant of pi over 3 is 1 over cosine pi over 3. I have to be in radians. Is just 2. So 2 cubed is 8. 8 over 3 minus 2 minus 2, 1/2. So it's 1/2 to the power 5. So 1/2, 1 over 2 to the 5 over 5. So this is going to be 1 over 2 to the 4. And then I'll just do what's 1 over 2 to the 4. 1 over 16. It's just 1 over 80. And, oh, sorry, I didn't even check what 0 is. Cosine of 0, oh, cosine of 0 is 1. Yeah, so I should actually check it. Minus evaluated at 0. So 1, secant of 0 should also be 1. 1 over, cosine 0 is 1, so 1 over 1 is 1, yeah. So it's going to be 1/3 minus 1/3 minus 1 minus 2/5. And I'll just plug this all into my calculator. 8 over 3 minus 2 minus 1 over 80 minus 1/3 minus 1 minus 2/5. I get, well, 413 over 240. Let's check that answer. Let's check that. Okay, I guess I'll do it. Wolfram. So integrate from pi over 3, sorry, from 0 to pi over 3, and integrate what? I'm going to integrate a fraction, which is going to be, I don't think I'm allowed to do sine cubed, but I'll put a cubed here. Sine x cubed over cos to the 4, not cos of 4 to the 4, cos x to the 4, plus sine 2x cubed cos x cubed dx. Looks right. 413 over 240. Is that what we said? 413 over 240. Yep, we're good. So there you go. That is the answer. Okay, guys. So let's move on now to, unless there's any other questions from the chat that I can do. Otherwise, let's move on to chapter 5. So let me find that quickly. I have too many circuit stuff open. There. Let's move on to chapter 5. 1 and 2. With, sequences and series. So I'll go through each thing here. And we'll go through. Yeah, we'll take it part by part. So first of all, 5.1. Yeah, so let's check what we're going to do. 5.1, 5.2, 5.3, 5.4, and I think that's it. We'll leave 5.5 and 5.6 because they're relatively straightforward. 5.5 and 5.6. Relatively straightforward. After that, we'll do some things. So yeah, so 5.1, 2, and 3. And 5.1 and 5.2, there's not too much there.
Is it on Adam hanging out only for me or?
Lagging?
It's lagging for me at least.
Yeah,
it's not lagging for me.
His
camera for me either.
It's only frozen on my screen. It's not moving.
It's just whoop, my phone fell. It's just the it's just your internet probably. I don't know.
I mean, the camera's a bit behind, but
yeah, that's what happened to me. Like I used to be in my room, like the farthest point from my router, and then I came downstairs, it's perfectly fine. So it's probably just your router or Wi-Fi.
Probably. Okay, let's move on to 5.1 then. So 5.1 is sequences. Right? Sequences. So in general, we're talking about sequences. Sequences is an infinitely long list of numbers that has an initial element. That's pretty much what it is. There's a bunch of different kinds of sequences. Sequences can be defined by a function, in which case you say it's an explicit formula for the sequence. For example, the sequence an is like 2n plus 5, right? And so you can find any term in the sequence. Usually the first term is like the 0th term or the first term. I'm going to go through this very generally. We have, yeah, what else do I say? Okay, arithmetic sequences are sequences that have a common difference. So like 2, 6, what did I go up by there? 4. So 10, 14, 18, you go up by 4. That's an arithmetic sequence. A geometric sequence, which is more important, is one where there's a common ratio. So that means that if you have like 2 And then it's going to be like 4, and then 8, 16, da-da-da. That's a geometric sequence. Mathematically, that is that for a geometric sequence, an over an minus 1 is some constant r. And for an arithmetic sequence, an minus 1 is some constant d for any term, for any n. That's the definition there. Okay, that's that. So we have sequence limits, taking the limit as, let me see here. Yeah, this is about everything you'd expect. So we have a sequence limit. So if I, probably better to do this as an example. Sequences, let's see an example. Find explicit formula, that's fine. Oh, we have recurrence relations. Let's do this quickly, I guess. Recurrence relations. So a recurrence relation is a way to define a sequence. So for example, if I say a1 equals 2, and then an equals negative 3 an minus 1, for n greater than or equal to 2, right? Then I can write out the sequence, right? The first term is 2. Then the second term is going to be, plug 2 into here. A2 is going to be negative 3 times the last term, right, which was 2. So negative 3 times that is negative 6. And then again, the next term is negative 3 times the last term, which is going to be 18. And then the next number, which I can't do in my head so fast. That's going to be the first few terms of the sequence here, right? And then, so to figure out in general what's going to happen here, well, I could write this as negative 3 times 2, right? And then I could write this as negative 3 times negative 3 times 2, right? So in general, that's going to be this was the first term, the second term, and the third term. So in general, that is, if I'm on the third term, then I'm going to write negative 3 to the 2 times 2. And I'm on the second term, I did negative 3 to the 1 times 2. And here I did negative 3 to the 0 times 2. So I can write this as negative 3 in general. an equals negative 3 to the n minus 1 times 2. And to check that this is right, though, like that was just kind of guessing. To check that this is right, I plug this into here and show left side equals right side. Right? So if I plug it into here, an is negative 3 to the n minus 1 times 2 equals negative 3 times an minus 1. So it's going to be an negative 3 to the n minus 2, right? N minus 1 is minus 2 times 2. And again, show left side equals right side here. Well, that's not too hard because negative 3 to the power 1 is going to add on there. So it's going to be negative, well, just that side is going to be negative 3 to the n minus 2 plus 1 times 2, which is minus 1, which equals left side. Therefore, this recurrence relation as an explicit formula is, I guess I'll write the 2 in the front, negative 3 to the n minus 1. So any questions about this example I just did there? I did it fast because I want to move on to the other stuff. I'm sure like we're pretty familiar with sequences, but if you have any questions about this, don't worry. Like we'll figure it out. And yeah. So okay. So then I will just keep going. So limit of sequences. If I had to find some sequence like this here, an equals 5 minus 3 over n squared, and I ask what's the limit of this sequence, we only ever take the limit for sequences as n goes to infinity. We want to know what's the infinite term of this sequence, right? So you can literally take the limit as n goes to infinity. So limit as n goes to infinity of 5 minus 3 over n squared is 5. So as n gets bigger and bigger, the term gets closer and closer to 5. Similarly, let's take a look at another example of this, which is 2 to the n over n squared. Right, 2 to the n over n squared. So an equals that. And again, I'm asking, what's the limit of this sequence? So I can literally take the limit as n goes to infinity of 2 to the n over n squared. Now the denominator is 0 and the top is infinity, so it's infinity over 0. This is a L'Hopital's rule situation. So I can apply L'Hopital's rule. It's going to be ln 2 to the n over 2n. Still times the limit there. And then I'll take L'Hopital's rule again, and it's going to be ln, my face is probably covering. So I'm going to take L'Hopital's rule again. It's going to be ln 2 squared 2 to the n over 2. Now finally I can take this limit, and this is infinity. So therefore the limit does not exist. Limit does not exist. So this sequence doesn't have a limit. If I keep putting in bigger and bigger numbers, the value just keeps getting bigger and bigger. This sequence, if I keep putting in bigger and bigger n's, it gets closer to 5. So yeah, there we go. Okay, so let's take a look. Limits involving continuous, that's fine. There is the squeeze theorem, which is probably worth something, but let's actually take a look at my mini test on this and see if that's anything of note.
I'm pretty sure on the mini test for this one, you had to apply the squeeze theorem.
Yeah,
Yeah.
So probably good. Oh yeah, it was a really short mini test. I remember that.
Yeah.
Yeah.
I remember
Just do the first one with 2
solving it
questions.
and not applying it, and I lost marks. But like, you know, those questions that are simple that you're overthinking it.
Yeah.
That's what happened. I was just like, I mean, this is the answer. I just don't remember how I came by
I
it.
think the
Yeah.
mini test is best, or the squeeze theorem is best done like when you build a function. Like if you want to find the upper and lower bounds of a function, you like start with like if you have a cos of something, cos x in the sequence.
Yeah.
Yeah.
Yeah. I'm just looking at the questions here. Okay, so actually, mini test 5 had 2 questions. It was part A, part B. So part B is from 5.2. So we're gonna actually wait until we cover 5.2 before I do the mini test. But yeah, so there is a set of definitions now after this, and it's as follows. So I'll just read through it. Everybody should know when I say these words. Hopefully you'll understand what I'm saying. So the following is a list of definitions regarding sequences. Say that an, the sequence an, is bounded above if there is some m where an is less than m eventually. Show this by inspection, or show that this inequality is true for some m. If you have a feeling of what m should be, then just show that's true. Or take the limit. Well, no, not necessarily. Bounded above doesn't necessarily mean the limit. But yeah, show this by inspection. Bounded below by the same thing, an is greater than, some value m eventually. And when I say eventually, it means that the sequence could technically go like this. If I were to graph the sequence, the height is the value of the sequence, and that way is the term number. If we say like the sequence is bounded above at, let's say 2, right? That can be true even if it goes like this, right? And then sort of flattens out and never goes above 2 anymore, right? That's what eventually means. It means that the early behavior doesn't really matter. The later behavior is what matters here. So eventually means that.
It's kind of like in high school where you could cross horizontal asymptotes, but
yeah, it's still exactly.
Eventually it would kind of go above or below, but it would definitely be bounded above. I'm bounded by that asymptote.
Yeah, exactly, close to that for sure. So yeah, it's just called bounded if it's bounded both above and below. Okay, so there you go. It's increasing if this is true, and you can show that by actually showing that this is true for all n greater than some k, which is some value, whatever, for all n greater than, maybe all n greater than 1, and then it's the whole sequence. Or you can show that f prime of x is always positive for all n or all n greater than k for some k. So what that just means is that you can turn the explicit formula into a function, show that the derivative of that function is always positive, which means it's always increasing past some value, past some critical point, right? Decreasing is very similar. Show that the derivative is always negative, or show that this inequality is true for some section of the number line. And then the sequence is monotone if it's either increasing or decreasing. And then finally, monotone convergence theorem is just saying that if AN converges, then it's bounded, and if it's both monotone and bounded, then it converges, which, if you think about that for a second, makes sense. So if our sequence converges onto some number, that means it must be bounded by something, right? And if you're both monotone and bounded, then it converges, which makes sense too, because look, monotone means you're only ever increasing, and you're bounded. Sorry, monotone means you're only ever increasing or decreasing. But if you're bounded, that means you have an upper and lower bound, right? So it doesn't matter if you're increasing or decreasing the whole time. Either way, you're going to run into the bound, and you're not going to be able to turn back up because you're monotone. So it must converge. And that's essentially it for 5.2. So let's take a look at that's it for 5.1. Now we're going to look at 5.2, which is series. Okay, series. Let's see what this is.
Is there anything in just basic series, or is it just like we go straight to comparison tests and stuff?
There is stuff in basic series. There is stuff there. I'm just looking at my notes here. Yeah, there is stuff. So essentially, first of all, the definition of a series, which is just that it's a sum. So if I have some AN, right, and then that's equal to A1 plus A1 is equal to a set A1, A2, A3, ... until infinity, really, right? What if I added all these together? So the sum n goes from 0 to infinity of AN equals SK, right? Or not SK, sorry, that's just S. So that's the series related to this sequence. So the series is the sum of all the terms of a sequence. You can take a partial sum, which is SK, and that just means you stop at some point. N equals 0 to K of AN. And so there's that. Let's take a look here. Sometimes you can find a formula for the partial sums, but a lot of the time you can't. Most of the time you can't. If we do find a formula for the partial sums, then we can say, so if we find a okay, so if the sum n goes from 0 to k of AN is some nice function sk, or s of k, call it s of k, right? If we can actually find a function of that, then if you take the limit as k goes to infinity, right, it's going to be n equals 0 to infinity of AN equals s of infinity. And so if you can evaluate s of infinity, then you can say that this sequence, this infinite series, is equal to something. And that's what it means by converges. So it converges onto some number. If this infinite, if this formula for the partial sums of this series has a limit that exists as you go to infinity, then it equals some number. But that's also not the point of what we're doing most of the time in this course. So we're not trying to find what the infinite series equals to. We're just trying to determine if the infinite series converges or not, if it has a value that it converges to or not. So that's most of the time what we're going to deal with. Let me see here quickly what we have. So we do have 3 special examples of series. So one's called a telescoping series, right? Telescoping series, right? Oh, it is 8 o'clock. So let's just finish. I'll just finish explaining this, and then we'll do the. Maybe we'll do. It's still light, so I don't know how late we're supposed to go. But anyways, we'll just a few more minutes, and then I'll stop. So telescoping series is essentially a series where some of the terms cancel. Oh, Siri's turning on. So if I get an example from the textbook, probably that's better. So if you're confused about anything I'm saying, I'm going through it really fast because, again, we're pretty familiar with this stuff. But by all means.
The mini test had a telescoping series question.
The mini test did have a telescoping series question. So maybe actually I'll just leave it for the mini test. Telescoping series. You'll see exactly what I mean by telescoping series there. So then there's arithmetic series. Yeah. And so then the only other part that's actually important to this in this chapter is a geometric series. Right? So a geometric series is essentially if I have the sum n goes from 0 to infinity of some ar to the n minus 1, right? Or ar to the n, doesn't really matter. So, yeah, actually it would be not n minus 1 here, it would be n. So that means this is a geometric series, right? This is the first term, and then each time it's getting multiplied by some constant ratio. This is equal to, well, first of all, it's equal to Ka for r, oh, sorry, sum goes to K. N goes from 0 to K. Is equal to Ka for r equals 1. Otherwise, it's equal to a1 minus r to the k over 1 minus r for r not equal to 1. And then if you take the limit of both sides here, the infinite series, n equals 0 to infinity, of ar to the n is equal to a over 1 minus r. And this
that
is
first
only
one you're talking about
yeah.
Sorry, for that first one you're talking about a partial sum, right?
Yeah, partial sum. Partial sum goes to k, right? Goes to k.
I don't know if this matters, but in the Bipolite, it says that the summation of infinity, where n is equal to 0, ar to the power of n minus 1 is equal to a over 1 minus r. But I don't know if that does anything.
I think it should be 1 on the bottom if it's n minus 1. It should be a 1 here. Is there a 0?
Oh, a 1? Okay, if it's 1, then... Okay, yeah.
If it's 1, then it's n minus 1 here. If it's 0, then it's just n.
Oh, okay. Thank you.
Because you want the first n value to be 0. That's the point, right? R to the 0. So that's how you do it either way. Okay, there we go. So that's that. Let's see now. I guess let's do. Well, it's 8:07, so let's take our break now, I guess. And then we'll be back. We'll be back at 8:30. Let's be back at 8:30, and then.
I just wanted to ask one more question. What if it was like n is equal to 2, so then it'd be ar n minus 2, ar to the power of n minus 2. If n was.
I guess so. Yeah.
Starting at 2.
So. Yeah.
Okay.
We've never really seen that applied because it's just usually just start.
I just wanted to make sure.
Yeah. That's right though. You would put that there to make this make this equal here. We do actually do that when we get to power series. We do kind of have to deal with that. So.
Yeah.
Okay, guys. So let's take a break until 8:30. Let's take a little bit longer one, and then we're gonna keep going after that. Finish the sections up to 5.3, no 5.4. So we're gonna do just the 2 divergence test, integral test, and then the comparison test. Spend a little bit of time doing that, and then we will do some more practice. So hopefully between 8:30 and 9 o'clock I can finish the rest of chapter 5 that we want to do, and then after that we have an hour of doing the practice tests and whatever. So
can we, if possible, can we try to find the domain of a function of more than one variable, like 2 variables?
Sure. Yeah.
That was a good question.
Sure, we can do that at the end. Yeah, we can do that at the end. That would be closer to the end, but yeah, definitely do that.
But we didn't receive the mark for the mini test, did we? No, we did not.
Oh, we did not. So I can't do the mini test, but I can do questions related to it, of course.
Yeah, that sounds good.
So yeah.
Thank you.
No problem. I'm just gonna check this quickly.
For the one with domain, we did get that marks back though, for mini test 11.
Yeah. I don't remember what marks we got back, but yeah, is that right?
We just don't have the last one, mini test 12. We haven't gotten that yet.
And what was on mini test 12? I forget.
It was just a simple chain rule, and like partial
Very
derivatives.
chain rule thing.
Oh, so it was on mini test 11. So we can do it because mini test 11.
Yeah, we did do mini test 11. Yeah, mini test 11's back, so we can do that question. Okay, so I will say back at 8:30, and there we go. So 21-minute break. Okay, so back soon, guys.
Quick question for you guys. Am I the only one, or like his brain is saying, just submit it, man. Just submit it. It doesn't matter. Just submit
It happens sometimes. It happens.
Submit what?
Your
Like a
exam,
test.
just submit.
Yeah,
just submit.
Yeah, happens a lot to me.
It won't hurt you anymore. Just submit it.
I don't get the context really. What do you mean?
In the last two questions, I just used any, meeny, many, mo. Okay, this question, this answer looks nice. Submit.
I've done that before because I'm too lazy to go check over my work. I do that all the time. It'll be the downfall of me. But I don't check my work.
Oh, I get what you're saying now. I've been punished for that already. Like I had more time, but I was like, just submit, and I missed some negative sign. I was just like, jeez, it hurts. But
how could I be wrong?
Oh,
I had my answer was $1,000 less than the options, and I said, nah, it's just probably just some error, some number errors. Choose that one.
Oh, for ECN, yeah. For the most part, I think the part that when I got that, I just went none of the above.
Yeah,
because I'm like at least one or two of them are going to be none of the above. There's 15 questions.
No. Anytime I put a lot of like 10 minutes into something and it give me something that's not there, I didn't even question it. I just put none of the above. I was just like, no, I don't want to. Like I'm not that invested in ECN like that.
It's only multiple choice. Why can't we have it duck right away? Just do
Yeah.
the auto grader and auto grade it.
Mm-hmm.
No, they like the suspense.
The last three questions were so hard. Like the bonus question.
It took a while. It took me over half an hour to finish over half an hour to finish the last 4 questions.
Yeah.
Is it just me that took a while to actually start the exam? Like I started it, but I was just so spaced out. I was just like, it was a morning exam, right? I was just like, what am I doing here again? And it took me a while, and I kind of paid for it because in the end, I was like, I needed the time at the end, but I was just like, just
wait.
this feels right.
If you started later, you didn't get a full 3 hours.
No. I'm talking. I started the exam, but when I was looking at the questions, I was just like, what am I looking at? It took a while for my brain to start actually using the content.
To get in the motion, right? To get in the motion.
Yeah.
I woke up at 7 that day, just to get my mind right before the exam. I woke up at 7 just to like relax, make sure my mind's on ECN. And
no, I was even there for the what Cameron had in the morning. I just still was out of it. I was not feeling, but I don't know why. Did anybody else feel really great yesterday after the exam? It was a Saturday. It felt very good.
It felt satisfying, yeah, definitely. After finishing that, I was like, yay. Because we're at 60%, so I was quite happy to get that over with. Now we got a 50% exam for ELE to deal with.
It can hurt us. It can hurt us. I can't say it can't hurt us anymore. It can.
Wait, if hypothetically, if someone's supposed to fail ECN, it's not like it's a requisite for something else, right? Or do you have to complete?
It's a required course. It's a required course, so you have to.
Oh damn. Okay.
It's just barely an engineering course. I don't know. It's run by the arts facility.
Yeah.
Art and business.
It's required, but you can, if you fail it, you can take it through Chang.
Oh yeah. Okay.
Yeah, you can probably do that.
Wait, do you have to pass the final calc exam to pass the course?
No. I'm pretty sure not, because 60% of our mark is the mini tests, and then 5% of it was a mini test 0, and then 25% of it should be the final exam. So you don't have to pass it.
No.
I mean, like, is there like a requirement that like in the final exam you have to get like at least a 50%? something?
Maybe implicit, maybe they wrote it out explicitly, but implicitly no. If you're taking account to the percentages, you don't have to pass it, but maybe they wrote it somewhere. I'm not exactly sure.
Right.
No, you don't have to pass the last like the exam. If you have more than 50, you're passing the course. There you go.
Wait, it says that on the course management form, right?
Yeah, I just sent it.
Alright.
Go to the discussion. And the final exam is 35 if you didn't do that, like if you didn't pay for the quizzes and the notes.
Okay, guys, I am back. Hello. Fix my hair a little bit so it doesn't stick out there. I have returned. Hello, I am back. So let's keep going from where we left off. It's 8:30, so we're probably going to go until 10 o'clock, like I said before. And we'll see how it goes. Any quick questions before I start? Start back up again. Get the question. Okay. So if not, then let's just get into it. So mini test 5 was this. Let's see here quickly. Let me get it. Okay. So show that the following sequence an, or what's the limit of the following sequence? Cos squared 14n. Right? Cos squared 14n. Okay, well, we know that cos squared, so we have to show, like, find the limit of the sequence is the question. Find the limit of the sequence. So we have to do this by the squeeze theorem, because essentially we're looking for the limit as n goes to infinity, as n goes to infinity, of cos squared 14n, right? So, oh, sorry, not this. 14n over 14n minus 9. Sorry, that's the sequence. 14n minus 9. Yeah. So, to begin here, well, we have to show that we know for a fact that cos squared, right? Cos squared, let me start with cos of 14n. Cos of 14n is between, oh, a fire alarm's going on, but it's just the toaster. Toaster gets hot, if you can hear that. We have a bad toaster. So, cos...
You won't burn anything.
No, it goes on all the time. Anytime someone uses the toaster, it goes on. So that's why it does that. So I know that this is true. -1 cos 14n to 1, right? That cos 14n is between -1 and 1. So if I square everything here, it's going to be, well, -1 square. Well, okay, let's just focus on this bit here. Or how do I do it? Hold on. If I square everything here, it's going to be cos squared is greater than 1, greater than 1. No, less than 1. Yeah, okay. So essentially, by squaring everything here, we know that cos of 14n is between 1 and 0. Right? Between 1 and 0. Because the maximum it can have is 1, and since it's being squared, it has to be also greater than 0. And that's the condition here. Divide everything by 14n minus 9. 14n minus 9 over 14n minus 9. And if we take the limit of these two things as the n goes to infinity, and if they agree, then that's the same thing as this limit right here. So technically greater than or equal to. So this limit is obviously 0. Then the limit on the other side is, let's see, well, as n goes to infinity, the denominator gets bigger and bigger. 1 divided by a bigger number is 0. So that means that the limit as n goes to infinity of this is 0. So the limit as n goes to infinity of cos squared 14n over 14n minus 9 equals 0. And the sequence converges to 0. Okay. Any questions about this?
Yeah, just one quick one.
Mm-hmm.
Can we say like x squared is just greater or less, like because we take the absolute value of both, it's just greater or less than 1?
Like you mean you don't want to use the 0 here?
Yeah. We just.
But squeeze theorem needs something, an upper bound and a lower bound. The squeeze theorem needs an upper bound and a lower bound. So that's you need to have both.
We're using that theorem where it's like if it's a bounded monotonic sequence. Not exactly, but it has to be bounded on both sides.
Yeah.
Makes sense.
Has to be bounded on both sides.
And
okay.
Also, yeah. Then the professor said it will be most likely between 0. I think it was most likely. One of the professors said it was most likely will be the limit will be 0 for this type of questions.
I don't know if the limit will be 0, but yeah, I guess here it'll be 0. For a squeeze theorem question, I guess they are kind of like 0, but yeah. Okay, then the next part of the question, same test, different question, is find what this series is equal to. N equals 1 to infinity of 1 over n plus 3 n plus 4 equals what? So, in other words, like this infinite series, what is the what are the partial sums? If you take the limit of the partial sums, what does that approach? So to get a little insight onto the series or the sequence, we can break the sequence up inside this sequence. We can break it up using partial fractions into 1 over n plus 3 minus 1 over n plus 4. Right? And let's take a look at this closely though. Right? Let's take a look at it closely. So S1 is going to be our partial sum up to 1. Right? N goes from 1 to 1. Right? So let's start here. It's going to be 1/4 minus 1/5. Right? 1/4 minus 1/5. Okay, S2 is going to be 1/4 minus 1/5, okay, plus 1/5 minus 1/6. One thing to notice here is that those terms cancel out. Let's take a look at S3. S3 is going to be 1/4 minus 1/5, plus 1/5 minus 1/6, plus 1/6 minus 1/7. Once again, these terms cancel out. So this is what it means to be a telescoping series, is that this is happening, right? In general, Sn is just, Sn is 1 over 4 minus 1 over n plus 4. And look at that, we have an explicit formula for the partial sums. Now all we do is we take the limit as n goes to infinity of Sn, which would give me 1/4 minus 0, which is just 1/4. Therefore, the sum n goes from 0 to infinity of 1 over n plus 3, n plus 4 equals 1/4. And there you go.
Can you repeat that last part that you said before with the Sn 1 over 4 minus 1 over n plus 4? You had said something after that. I didn't catch that.
Just taking the limit, I just said we have an explicit formula, so then we can just take the limit of the explicit formula as n goes to infinity, and that value is what the series converges to.
Okay, yeah.
And yeah, there's that. Okay, so that's that mini test done. Let's see the next one here. This one is going to be okay. So let's move on to chapter 5.3, which is the divergence test and integral test, which I'll just put on the screen, pretty much. So the divergence test is essentially... Question? No? Maybe not? Someone just unmuted for a second. Okay. So the divergence test is essentially just this. So if the limit as n goes to infinity of an does not equal 0 or does not exist, then the sum n goes from 0 to infinity of an diverges. That's it. That's the divergence test. So it's kind of like weeding out all the ones that are obviously not going to converge, right? So all the ones where the infinite sum, right, the infinite sequence, right, doesn't eventually go to 0, right? Because for a series to converge, you have to be adding a smaller and smaller term each time as you go further. Remember, this is the sequence I'm drawing, but the series is the sum of all these heights added together. So if we want that infinite sequence of the heights to approach to converge to a number, we have to be adding less and less eventually, and that's what the divergence test is saying. Right. Okay, so then that's the divergence test. Let's take a look at the integral test. So the integral test is just saying the following thing. So I'll just take a screenshot of this one. So that's essentially this right here. So the integral test is used for sequences with an explicit formula f of x, where the function is positive, continuous, and decreasing for b to infinity, wherever the starting point is, to infinity. then, okay, the integral from, you can determine if this converges, the series converges, if you take the actual function that's defining the sequence and integrate that from b to infinity. If that converges, then the other one converges too. But your function has to be positive, continuous, and decreasing on b. Technically, it can also be negative, continuous, and decreasing. Or negative, continuous, and increasing, I guess. No. It can just be negative, and... No, I guess it would have to be positive. Essentially, what I'm saying is just that if negative f of x satisfies these three conditions, then you can also use negative f of x as your f of x here. That's essentially what I'm saying. Then
So
that
it would
that
have
works.
to increase, like you want, if it's negative, it has to approach 0 as well. You still have to be adding less and less of a negative number, correct?
Yeah, that's for like the divergence test. In terms of the divergence test, yeah, to apply that, like that would be, that's the logic for that for sure. It's just that here to even do the integral test, you need these three conditions. So I'm saying just that if negative f of x satisfies these three conditions, then you can apply this test to see if it works, to see if it converges. All right, so these are the conditions to even apply the test. Okay, there's that, essentially. Let's try some practice of it. I think divergence test I'm just going to skip. It's just taking one limit. So the integral test, I'll do an example here. So I'll do 2x minus. Yeah, okay, I'll do this example. So we're going to determine convergence or divergence of the following series. The sum n goes from 1 to infinity of 1 over square root 2n minus 1. So let's take a look. Well, to determine if this converges, we have to look at the integral from 1 to infinity of 1 over the square root of 2x minus 1 dx. If this converges, then the other thing converges too. The series converges as well. I'll put example here. So
just
yeah.
Sorry for interrupting.
Okay.
Can't we, like, I know we're doing it for the example for the sake of the example, but can't we do p-test here and say since it's less than 1, it will diverge? I know we're gonna do it for the sake of doing it, but in the test, can't we say that?
P-test, like the p-series test?
Yeah.
Not necessarily. Let's see. What is the answer? Yeah, the answer is that it diverges, which matches that. I guess you can say that. Let me think for a second. Yeah, I guess you can say that. I don't know if that's exactly enough to prove it, because this is actually showing it, but yeah.
Does that work with an expression instead of just n?
I don't know if it works always, because I think they would have explained it to us if it works always like that. So maybe in some cases, in most cases, it does. But yeah. So just to get a feeling of if it should converge or not, yeah, you're right. The highest power of n is 1/2, which is less than 1. Less than 1. And so since it's less than 1, or less than or equal to 1, then it diverges as a p-series test.
Yeah, but we're not sure, so it will be more safe to do the integral test.
Yeah, exactly. The integral test will give you an actual answer.
You could use a root test, right? On this?
No, you wouldn't do it on this because the root test is for anything that's like to the power n, That's where it's useful.
But I mean, anything to the, anything, 1 to the power anything would be the same thing as this, right?
Sure, but then on the bottom you don't have a power n here. Here, that wouldn't help you on the bottom, because then you just end up with the nth root of this. And that's only useful. Yeah.
The entire thing. You could just square root the entire thing and say that's the power of the entire thing.
Yeah, like square root of n here, like nth root of this whole thing, right? But again, it just this denominator doesn't get simpler because of that. The root test is useful when the denominator gets, or when some part gets simpler because of that.
Oh no, I mean like that same square root, you could just put that on the entire function.
Like,
because
yeah,
like you could just like remove that. I'm just asking about the root test. You don't have to do it, but like, the square root on that 2n minus 1, you could just remove that and then say the entire thing as a square root.
Oh, so entire thing is under the square root like that. You're saying, yeah.
Yeah.
And then do the root test to this.
Yeah.
It's just that the root test is useful if the whole thing was to the power of n. That would be useful, right?
Mm-hmm.
Is because the root test is doing the nth root of something. So the nth root and the power of n cancel, right? But here, nothing would cancel. You would just have the nth root of the square root, and that doesn't you can't simplify that. You can't simplify that in any way, right?
Yeah.
Right, that's the problem. Okay, so integral from 1 to infinity of that. See if that converges or diverges. So let's take a look. See how we do it. Oh, 1. What? 2x. 2. Oh, okay. This is simpler than I realize. How do you... Oh, yeah, it's just one u sub. Never mind. I was like... For some reason, u sub was not coming to my mind for this one. I was like, I thought there was something more complicated happening. Okay. Limit as b goes to infinity of the integral from 1 to b of 1 over... well, I'll say root u. 1 over 2 du. So I just did a u sub there, right? I chose u equals 2x minus 1. Du equals 2 dx. Yeah.
I'm so sorry for interrupting. Sorry for that.
It's okay. Don't worry. Yeah.
Don't we have to show the requirements? Because Professor always said we have to show the requirements.
You're right.
Points.
I just didn't do that because I know we're in the integral test section, so I knew it applied. But yeah, you're right. We should show everything. So, is the function f of x, which is...
Sorry.
Don't worry. Yeah, that's good. Good note.
Was he asking about like proving that it's positive, continuous, and decrease?
Yeah.
Oh, okay.
And decreasing. Okay, so first of all, is it positive? Yes. Because 1's positive, and this will always result in a positive number, so it's positive. Is it continuous? It's continuous on the interval we care about, so yes. Well, actually, it's not continuous at 1/2, which is in the interval we care about, so it's fine. Is it decreasing? Yeah, as x gets bigger, right? As x gets bigger, this denominator gets oh no, hold on. Is it decreasing?
Yeah.
Yeah. It would be decreasing.
The derivative will be negative of it.
Derivative would be negative, that's true. And then also, yeah. As this denominator gets bigger, that means the whole value of the function gets smaller. So yes, it's decreasing.
Yeah. Right. We can say b to the n, bn is less than bn plus 1, right?
Yeah, and then you can also show it like that. Right? Yeah.
Oh, yeah.
Bn is less than bn.
No,
yeah, bn is less than bn minus 1.
The safest bet is to always just do the derivative.
Yeah, that is.
Because you'll always get the correct answer.
Yeah.
So the derivative is negative. Yeah. It's a rational function.
Yeah. So this is just going to be so 1/2 times negative 1/2 plus 1/2 is going to be root u divided by the new exponent is 2. So that's going to cancel. And then this is going to be evaluated from 1 to b. So I'm going to do right away root 2x minus 1 from 1 to b. So this is going to be the same limit as b goes to infinity of the square root of 2b minus 1 minus the square root of 2 minus 1, which is the square root of 1, which is 1. And now limit as b goes to infinity, well, this is divergent, right? This goes... this equals infinity. So since that means that the integral diverges, this diverges. Right? So therefore the series diverges. Okay. Any questions about this?
Just one quick question. The integral was of 1 over u to the half, right?
1 over u to the negative half.
Negative half. Okay. Well, No, wouldn't it just be? Would it just be half since it's 1 over already? Yeah.
Oh, sorry, yeah. 1 over u to the half. Yeah, yeah. Sorry. I was imagining just u to the, forgot the 1 over. Yeah.
Yeah, we just did the integral. But isn't B1, like, isn't it from the starting of the summation? So it's, and it was from 1. So isn't B1? Isn't it B to infinity? Or did you substitute infinity for B?
No, like, are you asking at the end here?
Well, either there or 2 lines above, yeah.
Yeah, well, it's just b is the variable that's going to infinity.
Okay.
Right? That's
it's
why
because in the
limit.
yeah, not because in the if you go in the note section, it said from B to infinity, but I think I get what it's saying now. It's like it's starting at B.
Oh yeah, sorry. Then I should use a different letter here. I'll use A there. Yeah. I'll use different. Not related to that B in the notes. Yeah.
Because like B would have been 1 in this case, right?
B is
in
1,
this...
the starting value. Yeah.
Yeah. Okay.
Yeah. That's right.
Great. I'm not crazy. Good.
No. Good. Okay, so that is essentially all of 5.2 and 5.3. There isn't a mini test on this stuff, I don't think. The next mini test we have is, comparison test. So let's get into that and the comparison test. Let's spend, hopefully just about 15 minutes on comparison test and try to do some practice. And so I know I was rushing those first few sections in chapter 5 because I want to get to this, and then we can spend more time on practice exams and all that stuff. So the comparison test is this. So if this is true eventually, then we have 2 different ways to determine divergence and convergence of the sequence. We can choose the Bn, right? We could choose the Bn. We're comparing it to something. And then here's limit comparison test. So in limit comparison test, they just both have to be positive, right? And then you can apply the limit comparison test. Here, one has to be greater than the other. So yeah, here one doesn't have to be greater than the other. It's just, you just have to compare them with the limits. But here, you one has to be greater than the other. So let's try some textbook questions about this stuff. So let's start here. We'll do a good couple of these. Okay, so A is determine convergence or divergence of the following series. So n goes from 1 to infinity of 1 over n cubed plus 3n plus 1. So this is essentially, you can think of this like this. This is our ANs. So I say our AN is 1 over n cubed plus 3n plus 1, right? And now we want to compare this to something that is either bigger or smaller than it, right? So I think that this is going to converge because I know the P series. So P series greater than 1. Yeah, P series greater than 1 is going to converge, right? Yeah. And so this is greater than 1, so I have a feeling it's going to converge. So now I can compare this to 1 over n cubed. But we have to determine which one's bigger here. Well, here, this one's always going to have, essentially we're trying to determine which one's AN is bigger than, or AN is smaller than BN. That's a question. We're not sure. So if I'm going to try to find this inequality. So if I start with just right now, n cubed equals n cubed, then I can also say that n cubed plus 3n plus 1 is going to be bigger than n cubed, right? 1 over both of these things. You flip the sign, n cubed, and we see that an is smaller than bn. So we know this now. An is smaller than bn. So if you look at the test here, an smaller than bn, that's what we want. Okay, and then so if bn converges, then an converges. If an diverges, then bn diverges. But we don't really care too much about this one. We don't want to determine anything about bn. We want to determine something about an. So we're going to use this first section. If bn converges, an converges. So we have to look at bn. Does bn converge? Yeah, bn converges. bn converges. because it's a p series. So since Bn converges, because of the limit comparison test, An also converges.
One thing that's weird about this though is that in the example where like you'll never in the function the An is considered what you're given, right?
Yeah.
So it's like why would I need to find what if Bn diverges if like I'm trying to find out if An diverges? Like I forgot how we used the second part of comparison test because like it kind of doesn't make any sense when you think about it right here. If we're given 1 over n squared plus 3n and that's An, and if it diverges, then we don't care about Bn. That's just my thought about it. So
yeah, we didn't, but we didn't learn anything about Bn here. We learned something about An, right? So we were looking here. We chose Bn. We know that Bn is always bigger than An, right? Always bigger than An, and they're of similar types. So if we can show that if Bn converges, right, then An also converges.
Yeah, I'm just saying. Okay, like the next example, when you get one, if An diverges, I'm just saying, like, what's the purpose of Bn? Because we're given An.
Oh,
Bn
I see
is
what
anything.
you mean. Yeah.
Yeah.
I see what you mean. Then in that case, you were given Bn. You were given Bn. And you chose an An that's smaller than it. Right? You chose an An that's smaller. And so you use that to show that the thing you were given diverges.
Also, it's just based. So it's just a terminology then, because it's just okay. Bn is what you're given in the second example.
Yeah.
And you're finding An. Okay. Yeah, that makes sense.
Okay, so the next one is the sum. N goes from 1 to infinity of 1 over 2 to the n plus 1. Well, okay, so this... I can't really tell if this is going to converge or not, but I know that I can pretty quickly compare this to 1 over 2. Bn is 1 over 2 to the n. So Bn is just our second one. Which one's bigger or smaller here? Well, I can do this pretty quickly. I'll put 2 to the n here. So 2 to the n equals 2 to the n. 2 to the n plus 1 is bigger than 2 to the n. And so 1 over 2 to the n plus 1 is less than 2 to the n. Sorry, 1 over 2 to the n. So we know that An is always smaller than Bn, right? So if Bn converges, then An will also converge. Well, Bn converges because it's a geometric series with a ratio of a half. So if you had a ratio less than 1, it may be a little bit more clearly. There we go. And so since the ratio is less than between -1 and 1, it converges, therefore this converges. Okay. There's that. Let's look at C. So C is looking at the sum n goes from 2 to infinity of 1 over ln n. So
are these the textbook answers?
These are textbook questions. These are textbook questions, yeah. That's right. So for this one, we want to compare. We want to compare this with 1 over n. That's what we're going to compare this with. Now, of course, I wouldn't think of that if I wasn't looking here. But one way to notice, I mean, you know, if you run into this now, you know, use 1 over n. But the reason that we can do this, yeah?
Yeah, again, I'm a big fan of Amir's video. He explained that, like, yeah. A line to the n is always, it has a less power than n, like the function n, the straight line n.
Yeah.
If you put like an x, just y equal x.
Yeah. Y equals x.
You'll see.
Sorry, what are you saying? I didn't catch what you were trying to say.
Yeah, you see how y equal x is just always bigger than ln to the n. So 1 over n, 1 over ln n is less than.
Yeah, but 1 over x and 1 over ln x, right?
Yeah.
1 over ln x is always bigger.
Yeah.
Exactly. Yeah.
It's the same inequality you did, but he used used the power functions to explain it.
Yeah. So we're just gonna compare this right now. Someone say something?
I didn't. I saw what he was doing. That ln of x is always bigger than 1/x, but I didn't get what he was trying to prove with the. I didn't get what he was saying.
we want to be able to see, like, we have 1/ln x here, right? We want to compare this to something, right? We want it to compare it to either something that's always smaller than it or something that's always bigger than it. So let's compare it to something that's always smaller. I mean, we could try with something bigger than it, but you won't be able to find much. So try something smaller than it. Then we have to decide something. You know, it has to be 1 over. Well, it doesn't have to be 1 over something. It's just going to be something that's always smaller than it. So start with the fact that ln x. If you graph ln x and you graph x, x is always bigger than ln x, right? X is always bigger than ln x. So start there. X is always bigger than ln x. So 1/x is always smaller than 1/ln x. And there we go. We found our Bn.
Oh, okay.
Right?
Oh, because it's like divergent, so we need a.
Yeah, we need something smaller than it, because now, yeah, exactly. We're gonna choose our Bn to be 1/n, and now we have to decide. Okay, does Bn converge or diverge? Bn diverges, since Bn's. Yeah.
Wouldn't Bn be 1/ln n and An be the? Isn't that the rule?
Oh yeah, I guess I know what you mean. Like, yeah, it doesn't really matter what you call it. The name doesn't really matter. It's just this is what matters. This is what matters here, that Bn is always smaller than 1/n. So since Bn's always smaller than 1/n, and it diverges, that means that An diverges. Therefore, An diverges. Right, and there's that. So, okay, there's that. That's all the questions from the book of comparison test. Of the main section of the book, obviously, not the whole book.
There were just 3 questions.
3 questions in the actual text. I'm not looking at just the practice problems. I'm looking at actually in the text.
Okay.
So then next we have limit comparison test, which is you just compare it with something. You don't have to worry about size. You just compare it with something, and something that's going to make this limit go nice. So you calculate the limit as n goes to infinity of An over Bn, and based on the result you get from that, then you decide what happens with it. So, for example, part A here, we have the sum n goes from 1 to infinity of 1/√n plus 1. Sorry, √n plus 1. So I'm going to compare this with 1/√n. So that's my Bn. My An is that right there. So I'm going to calculate the limit as n goes to infinity of An over Bn. An over Bn. So it's going to multiply by √n here. Right? And so this is going to be 1. That limit's going to be 1. And so since it's 1, we look at our examples here. Okay, well, what's happening? First of all, are they both positive? Yeah, they're both positive. If the limit is between 0 and infinity and exists, then they both converge, or they both diverge. Well, since this diverged, we got between 0 and infinity. This diverged, that means this diverges. And there we go. So the answer is it diverges.
I have a question.
Yeah.
Oh, yeah, I see what you did. My question is, if we used the other test that we just did, we will have no conclusion, right?
If we use the comparison test?
Yeah, we will have no conclusion, right?
1/n is always bigger than 1/... Yeah, we would have no conclusion. We would have no conclusion. That's correct.
We took the limit comparison test.
We did the limit comparison test, exactly.
So B of n is Bn is diverges, right, because of the P series?
Yeah, that's right.
Or did you? Okay, so then they both diverge.
Then they both diverge. That's exactly right. Yeah.
Thank you.
No problem.
Wait, so why would comparison tests not work? Maybe I'm not doing it right.
Yeah, so essentially we have Bn is always bigger, right? Bn is I'll just write it like this. This is Bn and this is An, right? Bn is always bigger. This diverges, which means that the sum goes off to infinity. That doesn't tell us anything about the lower one, though. That doesn't tell us anything about if the lower one should converge or diverge. If Bn converged, then you can kind of imagine like it's squishing it down and it's pinning it to have to converge. An also has to converge. And, or for example, if Bn, we don't know anything about Bn, but if we can show that An diverges, then you can kind of imagine it like it's pulling Bn up with it. I guess my camera's probably in the way, but pulling Bn up with it and it also diverges. So that's the only time you can learn something. If this diverges, you don't learn anything about An.
Yeah.
Okay. Part B is the sum n goes from 1 to infinity of 2 to the n plus 1 over 3 to the n. So I'm going to compare this to 2/3 to the n. Now, which one's bigger? Well, this one's always bigger. Actually, it doesn't matter. We're doing limit comparison tests, so it doesn't matter which one's bigger. They're just both positive. That's all that matters. So let's do the limit comparison test. So it's going to be the limit as n goes to infinity of an over bn times.
It is the magnitude of an over bn, right? Or is it not the magnitude?
No, it's not the absolute value for this one.
Oh, okay.
It's not the absolute value for this one. Because you see, I can get. Oh no, hold on. Is it the absolute value? Maybe I'm wrong.
I remember it being the absolute value, but I don't know if that was this one or like the ratio and.
Ratio and root test have absolute values for sure.
This one is just as it is.
LCT doesn't have absolute.
So then, what do you do if it's less than? If you get the ratio is less than 0? It doesn't even say.
It shouldn't make a difference. It's only if it's a constant or 0 or infinity that it matters.
I guess just every other case is inconclusive. That's all it is. Every other case is just inconclusive. So yeah.
For
Okay.
the limit comparison test?
Yeah, for the limit comparison test.
I think the limit comparison test, yeah, as he said, if you had any constant except 0 and infinity, you have a conclusion.
Yeah. Otherwise, no
Constant.
conclusion.
Wait, oh, well, isn't it like if it goes to some number it's not equal to 0, then they either both converge or diverge, so you'd have to know one or the other?
Well, you have to know about Bn. They either Bn both converges, or the Bn and An both converge, or they both diverge if you get a number between 0 and infinity. Right?
Yeah. So you'd have to know if either An converges or diverges, or Bn converges or diverges.
And since we're trying to figure out An, we definitely don't know that yet. But hopefully Bn is something we can easily determine. If it this definitely converges. So there we go. There's that. So now here, taking the limit, I can cancel those two, and this is just the limit of 2 to the n plus 1 over 2 to the n. And how should I do this? Limit as n goes to infinity. This is going to be infinity plus 1, infinity over infinity. I can do L'Hopital, but how's that going to help me?
It's going to be
Or you
1.
could just divide 2 and like separate them.
Oh yeah, you're right. I can separate them. That's a good way to do it. Limit as n goes to infinity of 1 plus 1 over 2 to the n. This equals 1. Yeah, there we go. Thank you. That's good. And then, so since I got 1, that means they either both converge or both diverge, so they both converge, because Bn definitely converges, so An also converges. Okay, there's that. Good. And then let's look at C, and then I think that's the end of what I have here from the textbook. So C is going to be the sum n goes from 1 to infinity of ln n over n squared.
Adam, do you think we have enough time to go over the mini test 6? Because I was looking at the solution, and like where me and you both kind of got stumped it. I looked at the solution, and it's quite interesting, and I think that it's really it illustrates a good point whenever you're trying to look for a comparison, like a limit to compare it to.
Yeah.
So do you think we have enough time to do that?
Let's do it now.
Okay.
This last question isn't that good, so yeah, let's give it a try. I have the question
because it is kind of tricky, and like someone else brought up a good point where we had the bottom as the highest power of n was 1 over 2, so we knew that it diverged. That is proven when it came to this question.
Oh, I see.
For the solution of this.
Yeah. So for me,
I was looking over it and it was pretty.
Yeah, it was
It was
difficult.
pretty interesting.
Let's see
Yeah,
if
I
I
didn't
can-
get it, but I was looking at the solution. He says something that is like, it says note that any choice of the P series where the P is between 1 and the highest power of n in the denominator will work for the Bn.
I see. So they do just say what we were thinking there.
Yeah, so that shows that it is how it works.
Hey, what were you thinking?
So somebody mentioned earlier on that when we had a 1 over 2n plus 1, so 1 over root 2n plus 1 as a series that we want to have a limit comparison test to, they said the highest power of n is 1 over 2, so therefore it diverges, right? And we didn't know if that applied always. So I'm looking at the solution for any test. It shows that the main motive behind choosing Bn was because the highest power of n here was between 1 and the highest power of n in the denominator. So it does work.
Okay.
Which I thought was interesting because I wouldn't have thought it that way.
Yeah. Here, I just want to write out one rule that I had. I'm looking at our old. There was that rule for finding, choosing some P series that's going to be useful, and I remember some teacher or someone.
Yeah, it was Majid. He said, take the dominant of the top and bottom. Like the highest
power?
degree.
The highest degree
Yeah.
of the top and the bottom?
He didn't say highest degree, he said dominant terms in top and bottom. Like for example,
probably-
in this question, you take ln n squared from the top, and from the bottom you take n 3 over 4.
Well, it's not exactly n 3 over 4. It's going to be n 7 over 4 because you're multiplying them, right? But other than that, that's the two ones you do.
Yeah,
So I think what he means by dominant is the one that increases faster or decreases faster.
Yeah. Let me see this quickly. I had it written down here. So if you.
So again, probably Amer's video on that's probably really useful to watch.
That's true. Yeah. Okay, here. This is the I found it here. So it's saying if you have the sum n goes from 0 to infinity of something over n to the a, then choose your bn to be n. What? N to the no, it's supposed to be 1 over n to the. Sorry. That can't be right. What I wrote. Yeah, definitely 1 over. I don't know. I just wrote 1 to the. 1 over. Yeah. 1 over n to the 2a minus 1 over 2. That's what I have written here. That's the formula, which isn't exactly the same thing as what you were saying, but I think that will get us the answer here because it's n to the 7 over 4, right? So this would give us bn equals 1 over n to the 7 over 4 times 2 minus 1 over 2. So this is going to be 7 over 2 minus 1 is going to be 5 over 2. Over 2 is 5 over 4. Oh, which is not the same thing as what they chose in the solution. I thought that would get us the same thing they chose in the solution.
No, if it's 7 over 4, I think you're supposed to add 1 to the numerator and add 1 to the denominator. So you get 8 over 5.
Oh, so
wouldn't 7 over 4 still work since it's between the thing?
7 over 4.
No, I think if you use 7 over 4, it fails. Or it's inconclusive.
Inconclusive, yeah.
Oh.
Okay, so we're saying to do ln n squared over n to the 7 over 4?
Like, compare them. Whichever one is more increases faster is the one that you're trying to compare it to. I think that's what Buddha said. Like, that's the degree of what you're trying to look at. They give you a range. So
basically, the most dominant term is the one where, like, if you could basically, let's say you expand the denominator, you're gonna get like 10n to the 7 over 4 plus yada yada yada. Well, if you add anything to 10n to the 7 over 4, but it's in the denominator, that makes the number smaller. So you can technically just remove all the other terms except for the
Yeah.
most dominant term,
Yeah.
and it's larger. It's larger than the original, but that's what you want, because you're trying to prove that it's conversion.
Yeah, I see. On n squared. I'm just thinking if I chose n to the 3 over 4. Yeah, look, if I just chose 10n plus 1 here, bn is that, then if I did the limit comparison test, limit as n goes to infinity of ln n squared over 10n plus 1 times n to the 3 over 4 plus 1 times 10n plus 1 over ln n squared. These would cancel like that. And then I'd get the limit as n goes to infinity of 1 over n to the 3 over 4 plus 1, which is n
infinity.
Which is 0.
0.
Oh, but
we don't know the
yeah.
anything about bn. That's
There
the
you go.
problem.
So there we go. Then that didn't work. That's why that didn't work. Yeah. Okay. So that didn't work because we got 0 as the answer, and the limit comparison test is inconclusive with 0 as an answer. So, or maybe it's not inconclusive, but it's not an answer we want. Let's see what happens. If it's 0 and bn converges, then an also converges. Oh yeah, but we don't know anything about bn, so we can't do it. Yeah, that's the problem. Okay, I see. So, yeah, we can't have a ln then in bn, because we don't know how to deal with that if there's a ln in bn. Right?
Excuse me. Can we solve for bn and now can we like say that cn, like another term?
Yeah, you
and
could
compare
do
that. And
You
just find
could.
it.
That might be more trouble than it's worth, though.
So the way that I
Maybe.
simplified this was, I just know that the original function is going to be less than or equal to ln n squared over n to the 7 over 4. I can compare that with 1 over n to the 8 over 5, which is, because, like, it's, you take 7 over 4, you add 1 to the numerator, add 1 to the denominator, you get 8 over 5. If you compare it with that, you should end up getting ln squared over n to the something. And because that's like infinity over infinity, you can use L'Hopital's rule. You should get an answer that isn't 0.
So you're doing 2 limit comparison tests there. You're doing 2.
Yeah, I think there's
No,
easier
it's not
ways.
too. It's you're basically doing a bunch of comparisons and then a limit comparison.
Yeah.
If you guys have some time, I will just go to Prof. Majid, and I will just he did a similar question to this one.
Okay, so whatever the person before me said, like the comparisons, there's an easier way. So you can use Majid's rule, like dominant on the top and dominant on the bottom, and then you can just compare that. Like for example, for us, there's ln n to the power of 2 on the top, right? So I just compared ln n to n because we know ln n is always less than n, and I just subbed it in for n just to make my life easier.
Like,
So
yeah, exactly. That's what I was gonna say. You could like do n squared over 10n plus 1, and then we know that diverges, right? And then we can work with that. Is that what you're saying?
yeah, that's what I did. Yeah, and it worked.
So compare this to n squared over 10n plus 1.
No, not that. You should look for a P series one. You should look for example, for us, what's your dominant term? Don't know what your dominant term is.
Go back to the question.
Dominant terms from top and bottom.
But this would still work though. This would still work because I can do divergence tests on this, and the the numerator would go 0.
No, don't you get ln n squared over n squared? Then
ln n squared over n squared.
Like if you compare those, if you're doing a limit comparison test with those.
No, I just mean I want to determine. Yeah, no. I was gonna say I could just do divergence test on this, but no, you can't just do divergence test on that because that would get you infinity. No, yeah, that would.
Well, you could compare that to n squared over 10n, and then we could simplify that to n over 10, which is P series P equals -1, which diverges.
Oh yeah.
Yeah. Okay. So simplify that to this, and then cancel one of those. No, but then this doesn't. I can't do. I don't think this works. Are you saying use n to the -1 here?
Oh wait, hold up. Yeah, never mind. No, I see what you're saying. Yeah,
that won't work. Yeah. Okay. So just let me cancel. Let me just rewrite this, and then I'll just copy this.
I think it's just always better to find a P series if you can, and to the power.
Because you know it instantly. Because whether it converges or diverges, you know it instantly. So you don't have to worry about comparing each one.
So what are you guys saying I should choose for BN now? What is the BN choice?
Look in discussions.
Can you expand bottom? Then we can see the. If you expand the bottom, then we can see the dominant term.
Okay, expand the bottom. Yeah.
You get n to the 7/4. Because you're adding 1 plus 3.
Yeah.
3/4.
So 10 n to the 7/4. Da 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 da. And this is ln n squared. Okay. Then so we compare now.
Bn would be ln n squared divided by 10n 7/4.
Bn.
I mean, that's like the starting point. Like that's a starting point. You know that n is bn, an is less than bn now.
Yeah, ln n squared over what was it? N to the 7/4.
Yeah.
Yeah.
Again, we run into that issue where we don't know whether that converges or diverges, right? So if we just put a 1 over that, if you just do 1 over n, anything between 4/4 versus 7/4, if we choose any n to the power of that, we will get a definite answer. It is kind of tricky the way they did the algebra, but I don't think that should be too much of an issue. It's kind of subjective how you do the algebra after that.
How? But sorry, I don't understand. What do I do?
So it's a 1 over, instead of ln n squared, just do 1 over n to the power of anything between 4/4 and 7/4. So just n to the power of 1 between that and n to the power of 7/4, because that's your highest number.
Exactly.
You want something that's bigger than it,
like,
right? But
are you
you
saying
also want
like replace? Oh, okay, replace n with that. Yeah. Okay. Yeah.
The top can just be 1, and then the bottom can be anything that is between n to the power of 1 versus n to the power of 7.
Because that will be
that will converge, but it will also be bigger than our original function.
So I'm choosing a Cn, which is 1 over n to the.
You don't even have to choose Bn. The thing is, you don't have to choose Bn. Like just like the ln n squared, you don't have to do that. I think that's
okay. So this is our Bn. This is our Bn here.
Yeah, choose that as your Bn. That's what the solution says, and I think that makes the most intuitive sense. And you can just go from there because that bottom will increase faster than the ln n squared will. I'm pretty sure. And then you should be good from there.
How do you know that it increases faster?
Well, my CP, I think you're also in CP, right? He had said the same thing I was gonna say, that he said just if you see a question like that where you have n and n to some fraction in the denominator, you just get you multiply those two, right? So you add the power and then you have 1 p greater than 1 and less than that new power that you have, which is n times, well, in this case would be 7/4, and that or anything between that will work, and that's what you use, and then you just do the same. It will work because it will cancel the I can show you right here.
I just sent Magis as an answer in the homework help. Like he did a similar question, like kind of simpler, but
yeah.
So this is I solved the question and I got it that it converges.
It does, yes.
Yeah. So I used I don't know what we're trying to do with this question.
There's multiple ways. Like I think Puch also mentioned a viable way, right? Like it depends on the professor. You guys were being taught something else, and then I before was as well. So he didn't really give us a definite like kind of thing to look for. I guess I could say.
There's a billion ways. Why I actually mentioned the ln n squared stuff is because I just wanted you guys to know to find like a starting point. Like if you use Majid's method, then you get like a starting point, and then you can compare and do whatever and get a simpler function. Yeah, that's why I just wanted to mention it. Don't overcomplicate it, guys. Do whatever that seems right to you.
Okay, I'm looking at the solution.
In this one, in the mini test, I tried to use the integral test, and I had a very, very horrible integral, and I didn't have time to fix anything. So I just submitted what I had.
Yeah.
I tried to give up halfway through for the integral test, and realized limit comparison test would be the only thing. Didn't get that either.
It was a horrible, horrible thing. Let me show you. Let me show you what I got.
I thought this was the hardest mini test that we had.
Yeah.
Yeah, definitely.
I agree.
I actually also tried integral test. I can see it now. It was
Yeah.
it was a struggle.
It was.
Yeah, I would just send it to the homework help. See how horrible that integral was.
Adam, what mini test is this?
6.
Okay.
6.
Yeah. It's vividly ingrained in my mind after what I did.
Yeah.
I can't even think of it. I spend my time even trying to prove that the integral test is applicable.
Yeah, that's already too much. So, okay.
Yes.
I don't think so 2n squared 1n to the highest power there. And ln n there.
It says any choice of p series where 1 is between p, which is oh, 1 is less than p, which is less than 1 over n to the 7 over 5. At least that's what it says for me.
Yeah.
But like, do you know why that is? Do we
It's
know
the highest. That's what I was trying to say. That it's the highest order of n in the denominator.
But like why is
that upper
that
bound
works?
could be.
Like I get the idea, but like why isn't that works?
So the reason that it works is that our p series test, we said that it converges if p is greater than 1, right?
Right.
So if let's say we have an inkling that this will converge. Okay, let's say we have a random inkling that this converges. Right? I don't know how we would get that, but let's say we assume that we think that it might converge. So our number has to be between 1 and the highest degree of n in the denominator. Because if we choose something in between that number, it'll still be larger than this. It'll still be larger than this entire expression. It'll be simple, and we will know that it converges.
So in general, you should try to get the biggest term in the denominator that's or the biggest possible value of p that's still less than the denominator's exponent.
Yes. Yes.
I'm gonna have something like this tomorrow. I don't know why, but I feel like it.
Well, that sort of makes sense though.
Yeah, it does make sense.
Okay, so then
Isn't it just that I think someone just said it, you want something that's not greater than the function's highest n power, but you want something to be able to cancel everything else?
Yeah.
Like the thing is, it doesn't really cancel anything. It doesn't make the algebra simpler. It makes it a little bit more complicated, if anything. Because they do a lot of like confusing stuff for the rest of the solution, but
yeah. So okay, so this is I'm gonna go with the solution that's in my that's given to me on BitBelite here. So
like you will know that the rest of like when you I think if you divide through by the highest power, you will know that that's the only thing that's left apart from everything else is gonna go to 0, right? Something else.
You want to try the solution that I found, or do you want to or I don't know what we're trying to find out for this. I think we know how to solve the question. We're just trying to find the best way to do it.
Okay, I'm gonna go through now with the solution that is given to me in BitBelite here, and we'll understand there. So
it makes sense.
Any choice of a p series between 1 over n and between 1 over n and 1 over n times n to the 3 over 4 will work. Any p series between these things, but not including those two. So the one that they'd use in the example is 1 over n to the 13 over 8, which is only 1/8 lower than this denominator. Okay, so that's our bn. We're gonna limit comparison test this. So to limit comparison test, this is gonna be the limit as n goes to infinity of ln n squared over 10n plus 1 n to the 3 over 4 plus 1 times n to the wait a second, what? Times n to the, oh yeah, no, they do a couple steps in one there. What? N equals...
Oh, I forgot. For this question, if you actually chose the ln n one, it would have cancelled out the ln n and made the whole process much easier, I guess.
If I chose the ln n over...
Yeah, like ln n squared over 10, what? Yeah.
But I wouldn't know anything about that converging or diverging.
You'd have to compare that again to something
I'd have to
else,
compare
which is
that
just
again to something else, yeah.
yeah. So it makes the
So-
cancellation simpler, but it doesn't actually tell you anything.
Yeah.
You pretty much have to use a p-series in order to compare, or a geometric series, but that won't help you in this question, I don't think.
Okay, so there we go. N to the 13 over 8 is what I have there. That's fine. Okay, and so now to figure this out, we multiply by the highest power in the denominator, which is, so we divide by the highest power in the denominator. So the highest power in the denominator, yeah. The highest power in the denominator is, here, I'll write this over here, n to the 13 over 8 is going to be 1 plus 3 over 4, which is 7 over 4. So we multiply top and bottom by 1 over n to the 7 over 4 over 1 over n to the 7 over 4. So this simplifies to, so just multiplying by 1 here. So I'll say the limit as n goes to infinity of, okay, so then this is going to be 13 over 8 minus 7 over 4. I guess I can just look here. That's going to be ln n squared to the n to the negative 1 over 8. Sorry, times n to the negative 1 over 8 over, and in the denominator we get, so here, how do I get that? N to the negative 7 divided by n. Okay, let's just do it without looking at the solution, and then I'll be able to figure it out. Multiply these two things on the bottom. Let's do that first. So there's going to be 10 n to the 7 over 4, 7 over 4, plus 10n plus n to the 3 over 4 plus 1 times n to the, 1 over n to the 7 over 4. Right, so then this is going to become the limit as n goes to infinity of ln n squared n to the negative 1 over 8 over, now this is going to become 10 plus, and now this is going to be 1 minus 7 over 4, which is negative 3 over 4. So 10 n to the negative 3 over 4 plus 3 over 4 minus 7 over 4. Oh yeah, that's just negative 1. Yeah. So that's just negative 1. So this is going to be n to the negative 1 plus 1 over n to the 7 over 4, which 10 plus 1 over n 1 over n to the 7 over 4. Yeah, okay, that's fine. Everything's okay. 10, yeah, everything's right. That's fine. So now we can separate this into two different limits. We can separate this into the limit as n goes to infinity of ln n squared over n to the 1 over 8 times the limit as n goes to infinity of 1 over 10 plus 10 over n to the 3 over 4 plus 1 over n plus 1 over n to the 7 over 4. Okay, so this limit is 1 over 10, right? Because all these terms go to 0. So this limit is 1 over 10. So now we got to figure out this limit over here, which is going to just, let's write it again. So it's going to be 1 over 10 times the limit as n goes to infinity of ln n squared n to the 1 over 8. Okay, if I plug in infinity now, it's going to be infinity over ln infinity is infinity. So infinity over infinity, so we have to do L'Hopital. So let's give it a try. So it's going to be, with L'Hopital's rule, it's going to be 2 ln n times the derivative of ln n, which is 1 over n, over 1 over 8 times the times n to the 1 over 8 minus 1, which is negative 7 over 8. Yeah. Negative 7 over 8. And so now, let's see, limit still, of course. Okay, so the divide by multiply. Okay, also 1 over 10, I forgot that too. Okay, so let me cancel like a couple things here. So it's going to be 1, it's going to be 8 over 5 times the limit as n goes to infinity of ln n over n to the negative 7 over 4, 7 over 8 plus 1, which is 1 over 8. So n to the 1 over 8, which we are not too far from where we began, right? So it's just squared. So I'm going to just do L'Hopital again. It's going to be 8 over 5 times the limit as n goes to infinity of 1 over n over 1 over 8 n, 1 over 8 n to the negative 7 over 4 again. This 1 over 8 is going to go up to the top, so it's going to be 64 over 5 limit as n goes to infinity of 1 over n to the 1 over 8. There we go. And now this limit is 0. So I got 0 out of it, finally. And so since I got 0 out of the limit comparison test, what happens? If Bn converges, An also converges. So if Bn converges, wait, is that right? Yeah. Yeah. So Bn, does Bn converge? Yes, it does converge. So since Bn converges, An also converges, therefore An converges. And there's our answer. So definitely a hard question. Definitely a hard question. Yeah. But there you go. There's that.
This was the only mini test that I
This was the only mini test that what?
I run out of time on it.
Yeah, you ran out of time on it? Yeah.
The
Yeah,
only one.
It was a hard one. Okay, guys, so let's take a look now. Let's take a, at the...
You go to the bottom of it again and did you just like, cancel and then do L'Hopital rule twice?
I did L'Hopital rule twice, yeah.
But before that, all you did was with the thing that you found, cancel out the highest nth term, and then you did use the L'Hopital rule on the simplified thing, quote unquote simplified.
Sorry, what was
the
that? With the I canceled
so
here. I did another step canceling, and then I did L'Hopital rule again.
Oh. Okay. Wait, what do you mean you did another step of canceling?
Like here I did some canceling here with the powers of n to turn it into just n to the 1 over 8. Right?
Okay. Yeah.
And then I did L'Hopital's rule again here.
You just brought on the 1 to the 1 over n thing? Okay. Yeah,
to the bottom. Right, right to the bottom. Yeah. Okay.
Wait, can you slow down?
Yeah. Well, that's about it. That's the end of it.
Oh.
Did they give practice exam? I thought they gave practice exams. Or did they not?
They have it as
an old exam.
They gave an old exam, right?
But the old exam is only like the last part of the course back then.
Yeah, remember, this is the first time they're doing a culminative exam. So the old ones are not going to cover the whole course. They're going to cover whatever.
They're going to have midterm 1, midterm 2, midterm 3.
There, okay, I found it now. Yeah, okay. So final exam, here we go. Let's give it a try.
It will be only the last part of the course, though.
Yeah. So
I thought winter 22, winter 2020 was the entire course, was it not?
No. It was the same that we did the first semester. It was just like the parts after the second midterm.
Yeah. No,
it says here the course had 2 midterms, a trial exam and a final exam. No? Am I wrong?
A trial exam, which is count as midterm 3, not.
Yeah, and then the point is that the final exam wasn't cumulative. It was between the last midterm and the final exam. That's what we're saying here, right? So all the final exams that they gave was just, but not the whole course. Our exam is the whole course.
Dude, I've just been studying the final exam.
Yeah. So our stuff is also the whole course, right? So that's what. Yeah.
If you want to review one exam, you should go through the 3 midterms that they post: midterm 1, midterm 2, and 3.
Okay, so let's start this one. So here we have we're determining if this sequence is absolutely convergent, conditionally convergent, or divergent. State explicitly the name of any convergence test used. Okay, so it's an alternating series. Right away I know that also because it's asking for these kind of convergence, so we know what kind of convergence it can have. So an is equal to -1 to the n minus 1 n over n squared, n squared plus 4. Bn, which is the absolute value of an, is going to be just n over n squared plus 4. And so, what?
Excuse me. Sorry for that.
Don't worry.
Sorry for interrupting you again.
Don't worry. Don't worry.
If we use limit n to infinity a to the n plus 1 over a to the n, I forget what test that was. I forget the name of the test. Isn't it?
N goes to infinity of a to the n over a to the n plus 1.
Oh, a to the n plus 1 over a to the n.
Yeah.
Oh, that's the ratio test. That's the ratio test.
That's the ratio test. Yeah.
But
I forget the name
I think
of
it's
that, sorry.
easier to just do a limit comparison test for this.
Or alternating series.
Or just the alternating series test.
Oh no, we have to determine if it's absolutely convergent. So we can't use the alternating series.
You're right. Yeah.
I mean, we're gonna have to
do
use it
either
at some
one.
point because it could be conditionally convergent.
If it's absolutely convergent, though, then it's gonna be also conditionally convergent. It's up to, I mean, you can do either.
Then we will be easy to find the range of convergence if they ask for it, and no, we did not.
Okay, let's start here. Limit as n goes to infinity of bn. That's what we're looking for. That's going to be the limit as n goes to infinity. So this is the alternating series test. So bn, well, that's just going to be the power in the denominator is higher than the numerator, so I got 0 there, right? So that's going to give me 0 as the limit. Okay, then an converges. So an converges, but we don't know if it's absolutely or conditionally. So to determine if it's absolutely or conditionally, well, let's look at the definitions of those words. So an is absolutely convergent if the absolute value, if an converges, yeah. Wait, how did I write this? An converges, but absolute value an diverges. No, don't we already know? Don't we already know that this is, hold on, if bn converges.
We know bn does converge.
We don't, actually, sorry, we don't know that bn converges. Hold on, we don't know that bn converges.
But the limit as n approaches infinity is 0.
bn, why
doesn't
would
need to converge.
Say that
We should do the ratio test.
Hold on, too many people talking at one time. Let's one person at a time. So what? Yeah, who was talking there?
Yeah. Someone else was talking first. I'm sorry. It was.
Don't worry.
I was just going to say that we don't need to necessarily know like immediately now whether this series converges. I'd say that we should start with the alternating sign test, because at that point we know whether it converges at all, which it does just looking at it.
Yeah, so this would be it, right? I took the bn's, and they are the bn's are we know that by the alternating series test.
Yeah, what he's saying is like it's kind of more time efficient if we checked for the absolute convergence because if it's absolutely convergent, it is convergent.
Yeah. So to check for absolute convergence, but that's what I'm doing, isn't it? The bn's.
Convergence.
Oh yeah, just test for convergence of this. Test for convergence of this.
What he's saying is will be more time efficient if we did the absolute convergence first, because if it's absolutely convergent, it's convergent.
I see. Yeah. Okay, so now we're determining convergence of this, right? Of this series. And so we can do that by just doing by choosing b what?
The original series, not the bn that you create. The original series.
I'm sorry. Isn't it if bn is divergent, then you have to test an to see if it's convergent, then it would be conditionally.
Yeah, so this is bn. I have to test if bn's convergent now.
You're good.
Yeah.
At least I think.
This is what I'm supposed to be doing. Testing if this converges. If this thing converges.
Okay.
The exam, so we can use any. We're not limited to any specific test. So.
Yeah. So I'll do. What should I do now? I'll just compare. I'll just say Cn equals 1 over n over n squared, and then that's going to be 1 over n. So Cn is n squared. So Cn is always bigger than that. So if Cn converges, no, Cn diverges, so that doesn't help us. So I'll just do the...
You can use LCT, and it does help.
Yeah, okay, I'll do limit comparison. Yeah, okay. So limit comparison test now is going to be the limit as n goes to infinity of Bn, n squared plus 4, over Cn, which is going to be multiplied by n. So it's going to be n squared there. This is 1. So I got 1 out of the limit comparison test. So let's see what happens if I get 1 out of the limit comparison test. Then they either both converge or both diverge. So since Cn diverges, then Bn diverges. That means since Bn diverges but An converges, that means that this An is conditionally convergent.
Yeah. When did you actually test for An though? I didn't see that.
Right here.
Just one quick question.
Yeah.
Isn't it? Aren't we supposed to do the ratio test to find this if it's absolutely convergent, or we can use any other test to find it? I only used like ratio test.
Well, you can use any test because all you need to know is the table, right? I'll put the table here. So any type of test is good, yeah.
Okay, I didn't know that.
Right?
Sorry for that.
Don't worry. Yeah. So here we have, if An converges and Bn diverges, which is what we had right now. An converged. We did that by the alternating series test right here. And Bn diverged. We did that by limit comparison test. We concluded that, An is conditionally convergent. Right? Conditionally convergent. And by definition, that's what it is. Okay, there's that. Let's try the next one. If I can find it. There. Oh, I lost it now. I don't know where it went. Okay, next one here is... determine whether the series is absolutely convergent, conditionally convergent, or divergent. State explicitly the name of the convergence test used. Okay, well, I see an n factorial, and I see a to the power of n. So I'm going to use the root test for this one. So root test, right? So the root test is I take the limit as n goes to infinity of the nth root of the absolute value of n to the n over n factorial negative 3 to the n. I'm going to have the nth root of n factorial, which is a little strange. Oh, okay, so they've... Interesting.
Did you do this with a ratio test, or would you get a weird answer?
No, they do it with the ratio test in the actual question. Yeah, I guess that makes sense because the factorial, there's no other way to deal with that factorial. There's lots of other ways to deal with an exponent of n. Well, I mean, lots, but there's other ways to deal with an exponent of n, but there's no other way to deal with the factorial except by the ratio test. So I think we just have to use the ratio test here. If you see a factorial, you just have to. So
for the ratio test, is it n plus 1 to the n plus 1 for the top? You're changing every n to n plus 1?
Yeah, it would be n plus 1 to the n plus 1, yeah.
Oh, okay.
I was even going to say that when you did the root test, the n factorial can't really be included since it's not risen to n as well.
Yeah,
just negative.
It wouldn't. Yeah, you're right. It wouldn't help us at all. We wouldn't get far like that.
Yeah.
So yeah, so if we use an plus 1, so it's going to be n plus 1 to the n plus 1 over n plus 1 factorial minus 3 to the n plus 1 times an, 1 over an. So it's going to be n factorial times negative 3 to the n over n to the n. Okay, so now I can rewrite this as n plus 1 times n plus 1 to the n over n plus 1 times n factorial times negative 3 to the n times negative 3 times n factorial times negative 3 to the n over n to the n. N factorial and negative 3 to the n cancel. And let's see what we're left with. Oh, n plus 1 cancels. So we're just left with n plus 1 over n to the n. And again, sorry, I should be right. I'm taking the limit of all this as n goes to infinity, right? This is going to be... What'd you say?
Can you like apply like a second test in this? Because I remember Majid's doing stuff like this in his study hall. So I don't know.
But we're not asking if this converges or diverges. We're looking for the limit as this goes to infinity. So we wouldn't use another test here. Right? Limit as n goes to infinity. Limit as n goes to infinity. So you rewrite this as 1 plus 1 over n to the n. And I realize I lost the 3. I lost the negative 3. So there should be, hold on, lost the negative 3. So there should be a negative 3 on the denominator here. Negative 3. Oh, but it's not to the n. Oh, so it's just outside.
Yeah, so we can factor it
It's
in.
just outside. It's just outside here. 1 over negative 3. Yeah. Okay. So then this is just, like I said, 1 plus 1 over n to the n. Just times 1 over negative 3.
Isn't it 1 over 3 because you're taking the absolute of everything?
Oh, yeah.
So when you take
Wow.
it out
Okay.
of the absolute.
Yeah, you're right. This is all in absolute values. This is all in absolute values.
Good eye, good eye.
Yes, so that's positive 3. And then, that's right. So then we get e over 3. And so we got e over 3 out of the ratio test. So if we look at the conditions for the ratio test, it's, if we get a value, first of all, what is e over 3?
Well, e is like 2.7 over 3, so like less than 1.
Less than 1, 1.9. Sorry, 0.9. So we got less than 1, so that's because we're between 0 and 1. That means an is absolutely convergent. An is absolutely convergent. And there we go. Okay. Any questions? If not, I will move on. Let's try to finish this.
This.
What'd you say?
I just had a question. How
Was
did
on
you get
like,
E?
Go ahead. Saying something.
Oh, sorry,
Someone
I just
else.
cut you off. Sorry, I just asking. How did he get E? Like E over 3?
Oh, this
Yeah,
is
I
like
just wanted
this is an identity for E.
Oh.
That's just like how you define E in a lot of times, a lot of cases. Limit as n goes to infinity of 1 plus 1 over n to the n. That's just E.
Oh, okay. Yeah, I didn't know that.
Yeah.
Yeah, there you go.
I was saying something now on the previous question. At the end, like you had made some conclusion, and I was just kind of missed what you were saying. Like,
yeah.
What was was it that? Okay, go ahead. Yeah.
Well, so the conclusion that we made is that an converges. An converges, right? So that's by this right here. We saw that the limit of bn goes to 0, therefore an converges. Right? I guess I wrote that here too. What'd you say?
I was saying that's the thing, right? If bn goes to 0, then an converges, right?
Yeah, but then we also have to check if bn converges, because that'll tell us if it's absolutely convergent or conditionally convergent. So we look at bn, which was this series, right? bn. And to determine if that converges, I just compared it to 1 over n, limit comparison test, and I got 1. So that means that Cn, when I get 1, that means they both do the same thing. So if Cn diverges, then Bn also diverges. So Cn diverges, Bn diverges. That tells us that we have An converges, Bn diverges. We are conditionally convergent.
Yeah, it's just that because how I was thinking it is that usually we check for Bn first, and then if it's
that's true. Yeah, that makes more sense to do that. Yeah.
Because if it's convergent, then we just know that the entire thing is convergent. But if it's divergent, we check An.
Yeah.
Because I actually never thought of saying Bn goes to 0, An is convergent. I didn't think about that.
Yeah, no, that makes more sense. I don't know why I did the other way first. There's no real reason I did it first. That's just where.
Okay.
First, yeah. So yeah. Okay.
Yeah, I
have
had a question about that.
Yeah.
I have a question too. Sorry. So from that test, can we determine if it's absolutely convergent too? So if let's say Bn on that question was convergent, so then An and Bn would be convergent. So what that mean is
absolutely convergent. That means so look here. If Bn
Oh,
diverges, right? It's not possible for An to convert to wait.
Okay.
For Bn to diverge. So if Bn wait, is this table wrong? Hold on. What? If Bn
No, I think the table's just saying like An diverges and AN and B, AN and BN can't diverge, I think. Oh no. Yeah, AN can't diverge and BN converge, something like that.
If B and yeah, it's just a weird way that this is. It's kind of, I guess, as backwards is not good to do it. But if BN converges, and oh yeah, okay, this is what it's. Never mind. Yeah, I'm just tired or something. I don't know what's going on. If BN converges, it's not possible for AN to diverge. That's what it is.
Yeah. Okay. I got it. Thank you.
Sorry, I don't know what's happening. Yeah, there you go.
Okay, it's been a long day.
It's been a very long
evening.
Basically, just saying AN is convergent again.
Yeah. AN is definitely
convergent.
Yeah. Okay. Question 3. Solve the initial value problem. Let's give it a try. So I need to get y prime by itself, because this is a linear differential equation. So it's going to be y prime plus 2 over x squared minus 1 equals 1 plus x over x squared minus 1. Now, oh, so there's a y here. Then we can jump right to the solution. Y equals 1 over e to the integral 2 over x squared minus 1 dx. Then this is times the integral of e to the integral 2 over x squared minus 1 dx times p of x, which is 1 plus x over x squared minus 1 dx. Good. That is our solution. So let's integrate this. Well, the integral of x squared, 1 over x squared minus 1, that's tan, right? Let's check that quickly. But that's tan inverse, I'm pretty sure. No, that's plus. Oops. So then I need to just do difference of squares again and partial fractions. Is that what I need to do?
Yeah, that's what's in the solution.
So it's in the solution? Okay. So then let's just do that quickly. Integrate 2 times 1 over x squared minus 1 dx. That's going to be 2 times...
Keep the 2 in. It's going to help you.
Oh, okay. 2... Thank you. 2 over x plus 1 x minus 1 dx. Then we can do partial fractions on this. So 2...
Substitution.
A u sub?
Oh, wait, no, never mind.
I don't have an x on the top, right? So I couldn't do that. Right. So 2 equals a times x minus 1 plus b times x plus 2. Sorry, x plus 1. So 2 equals ax minus a plus bx plus b. So 2 equals a plus b x plus b minus a. So b minus a equals 2. So b equals 2 plus a. 2 plus a. And then a plus b equals 0. A plus 2 plus a equals 0. So 2a equals negative 2. A equals negative 1. B equals 1. So that tells me that we can integrate instead negative 1 over x plus 1 plus 1 over x minus 1 dx. Okay. And these are just two simple lns. Yeah. So this is just ln. Yeah, I see. Okay, ln absolute value x plus 1 plus ln absolute value x minus 1. That's all we need. Okay, good. And I can combine this. I can combine this now into a...
Isn't it negative 1? Because it's a is negative 1, so then would it be ln x plus 1 to the negative 1?
If it was the other way around, if it was 1 minus x, then it would have been...
No. I think are you just saying this negative up here?
Yeah, so then...
Yeah, I just forgot a negative there. Yeah, I just forgot a negative there.
Oh, I thought you meant for the x minus 1.
Yeah.
Just to be clear, if it was x minus 1 in the denominator, it would have been negative ln, right?
If it was 1 minus x... Oh, no. Yeah, if it was 1 minus x, not x minus 1. It is x minus 1.
Yeah, sorry, 1 minus x.
Can we do one of the domain questions maybe? Like
Yeah, we will. Let's just finish this question and then do that. So x plus 1 absolute value. There's our thing. So that means my integrating factor, well, you know what? It's just e to the that, right? In this equation here. E to the that. So there we go. This is going to be y. Oops. It's going to be y equals 1 over e to that, which is going to be x. Well, okay, so it's 1 over that, so it's just going to be. Do I ask? Can I drop the absolute values? Why can I though? I don't know why I can. But okay, x plus 1 over x minus 1. I can. This is going to be x minus 1 over x plus 1 times 1 plus x over x squared minus 1 dx. This cancels.
What you have is always will be positive because of the limit. It starts at n equal 1. It will be always positive. That's what you can do.
What did you say though? The limit? What limit?
Oh, we're doing another question.
Oh, okay.
I'm
Yeah.
so
Wait, you forgot the 2 before the ln.
What 2? Sorry?
So yeah, you see the ln x minus 1 over x plus 1? Wasn't there supposed to be 2?
No, the
oh,
2 came in here.
Yeah, never mind. I thought you did it with 1. That's why.
Yeah. So this is now x plus 1 over x minus 1 times the integral of x minus 1 over x squared minus 1. Well, x squared minus 1 can turn into x plus 1, x minus 1, which will factor. So this is y equals x plus 1 over x minus 1 times the integral. Not times the integral. Times ln absolute value x plus 1 plus c. There we go. So now I need the initial value. So since y of 0 equals 2, it was given to us in the question, y of 0 equals 2, then I can say 2 equals 1 over negative 1, so negative, ln absolute value 1 plus c. So there's that. So negative 2 equals, ln 1 is 0, so ln negative 2 equals c. And there we go. So our final answer is y equals x plus 1 over x minus 1 times ln absolute value x plus 1 minus 2.
Was it at x equal minus 1? Or is that is because you have a minus 1 in front? I was wondering where you got that from.
Because x is 0, so it's going to be 1 over negative 1.
Oh, yeah. Yeah.
Right?
Never mind me.
Don't worry. Yeah, there we go. Okay, let's see if there's any of the multivariable stuff to finish here. No, there isn't one where you like find the no, there isn't one where you find the domain.
Really? The final doesn't have a question like that?
They have find partial derivatives, do the chain rule, and then maximize on a closed interval, which is a long question. But yeah, no find the domain of. So I don't really have any new questions on find the domain of. Do you have whoever was asking me, do you have a new question on find the domain?
We got our marks back on the mini test.
When you say find the
you
domain,
want to do the mini test, yeah. Mm-hmm.
We can do that.
The mini test?
Yeah, the mini test one. Mm-hmm.
11. I think, yeah, we got the marks back, so we can use it.
Okay,
oh,
yeah.
That's when we had a graph. Oh man, that one sucked.
Yeah.
I had to redraw my graph in like the last 10 minutes.
Yeah.
See my graph was a sketch. My graph should never be considered a graph. It was a sketch.
Yeah.
No, it was not.
Yeah, I sketched. I'm not what? Who will graph that?
So here I have mini test 11. That's what we're doing. So the question was, consider the function f of x y equals sine inverse x plus 9 over 2 over You can tell I'm getting tired because I'm writing more crooked every time. Okay, everything's getting crooked. My head's crooked. The tablet's crooked. Square root of.
This is a safe zone. This is a safe zone. No one judges.
Oh, okay. Yes. Thank you. Yes. Ln absolute value x plus y plus 7. There we go. That's our function. What's the domain? Pretty much sketch the domain is the question. So, well, there's 3 restrictions, right? 3 restrictions. So first of all, the one that's caused by sine inverse. So the domain of arc sine is -1 to 1 inclusive, right? So that means that x plus 9 over 2 has to be between -1 and 1. So we find the restriction like this. Subtract 9 from both sides. -11 x -7. There we go. There is our first restriction. That looks like that. Our second restriction, so that was number 1. Number 2, our second restriction is the domain of the denominator. Right? So domain of the square root of 9 minus x, what was it? X plus 9 squared minus y minus 2 squared. Well, 9 minus x plus 9 squared minus y minus 2 squared has to be greater than 0, or greater than or equal to 0. So 9 to be greater than or equal to x plus 9 squared plus y minus 2 squared, right? And this is our next restriction. Oh, sorry, not equal to? Oh yeah, it can't be equal to because the denominator can't be 0, so it can't be equal to that. So there's our second restriction. Yeah.
So that's a circle, right?
That's a circle centered at -9, 2 with a radius
-3.
3.
Yeah, right.
You basically just graph, I mean, as far as I remember from the question, you just graph your 3 restrictions, and then there's your domain.
Yeah. And then our last one is the domain of ln absolute value x plus y plus 7. Of ln absolute value x plus y plus 7. Since we're taking an absolute value, x plus y plus 7, x plus y plus 7 just cannot equal 0. Right? That's the only thing that it just cannot equal 0. So what that tells us is that y cannot equal negative x minus 7. And there is our final restriction. So now you just graph this, which is much easier.
You have said that in.
What'd you say?
I'm not just saying. Shouldn't you have just said that in terms of x instead, or
why?
Actually, nah, never mind. It's in terms of x. Yeah.
We're used to seeing y equals mx plus b, so I just leave it as y equals mx plus b.
Yeah.
A half circle, right?
What'd you say? Sorry.
The domain will be within the half circle because the line it goes through the center of the circle.
Yeah.
I think.
Well, it's not a half circle; it's a full circle because it's not saying that we have to be greater than y has to be greater than some line. It just can't be on some line, right? Because it's not that this has to be greater than 0. It just can't be equal to 0 because it's in absolute values.
Makes sense now.
Right? Yeah. Okay, so we're gonna center our circle. Yeah. Is that what it is? Yeah. So it's not that we have to be greater. This quantity doesn't have to be greater than 0. It just can't be equal to 0. That's the only condition because you're taking an absolute value. So if it was negative, it would just be positive, and that's fine.
If there was no absolute value, then it will be just a half circle.
Then it would be greater than it would be a half circle. That's right. But here it's just like it's a circle, but there's a slice cut out of it.
Wait, are we referring to 2 of the domains where we're saying half circle or circle?
I'll show you when I draw it, and it'll make more sense if you're confused. It'll make more sense when I draw it. So -9, 2 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 2, and radius 3. So there is our circle of radius 3. That's our first domain. That's this. Well, I'll use our second one technically, but that's fine. X has to be between -11 and -7. So if that's 9, 10, 11. So -11 and -7 is right there. Okay, and then where's our line? Y equals -x minus 7. So it starts at -7, 1, 2, 3, 4, 5, 6, 7. And then it's just a straight line that comes up from it like that. So, in total, our domain is this section here. That is our domain. Not including the curved parts of the circle, not including the dotted line, but including the sides here. These lines count. These lines count. Now, if you want to see a better picture, I did it better when I actually did it. So, this is when I actually did it for the test.
Wait, did you use the OneNote like pictures, like
just
shapes?
the circle, just like the circle tool helped me a little bit there.
I was just like, hey man.
Yeah. And there we go. So that's that. Should I do part B as well? I guess I may as well do part B. So
the 3D of this ring, it will be like a rectangular, but with round edges coming out, right?
Yeah, like if you were to just draw the domain, it would be like this. Yeah, it would be like that with round edges, but then straight edges here.
It will be like a box with round edges.
Yeah.
Coming out of the screen or like down, because there's no restriction for Z, right?
Well, but the Z, there's no Z variable in the domain. The domain has no Z variable, right?
No, the Z is the output. So the f of x, I'm meaning.
Yeah. So we don't consider the output when we're talking about the domain, right?
Yeah. No, I'm just wondering how it will be if we like grab the 3D version of it.
Oh, if you were to actually graph it, let's graph it. I'm interested in what it looks like, so let's give it a try. GeoGebra. Let's graph it. I have it here. So f of xy equals fraction arc sine of fraction x plus 9 over 2 x plus 9 over 2 over square root 9 minus x plus 9 squared minus y minus 2.
Are you on the 2D graphing or the 3D graphing?
I am in the 2D graphing. Hopefully I can copy and paste.
Hate to see it.
I can copy and paste. Okay, good. Usually it doesn't let me, but that time it did. 1 absolute value of x plus y plus 7. And there we go. Ooh. There we go. That's the function. So, yeah, it's a little curved bit at the top. Kind of see what it looks like there. It's a curved bit at the top, straight sides, and then it has this discontinuity at x equals y equals 7. No, not x equals y equals 7. X plus y plus 7 equals 0. So it's not defined on that plane, but everywhere else it's defined. And yeah, so that's kind of what it looks like. Strange.
That makes sense.
Right, that's what it looks like. Okay, so then here, let's see. If we want to finish answering this question, the last part of the question was, is this point P in the domain? So P is -9 plus root 2, 2. Is it in the domain? So to check if it's in the domain, I mean, essentially we have to check if it's here. So you can do it graphically. So 2 is between 5 and here. So it's okay in the y. It's like it's on this line somewhere. But we have to just make sure that the x value is between -11 and -7. So just -9 plus root 2 is -7.58. So we're good. It's like right there. So there we go.
I don't remember. Did we have to like actually show that it did, or just like
It just said is the point. So why or why not? If you just explain it a little bit, then it probably is enough. I did the full explanation here when I submitted it. So if you want to just look at that quickly, this is what it.
No, I didn't think like I think what I did was just put it into the equation, showed that it was
defined. Yeah. What I did is just does it pass the 3 restrictions? It passes this restriction, passes this restriction, passes that restriction. There we go.
That was an easier way to do it. That.
And then it said find f of whatever. So we have now just going to take f of -9 plus root 2. So let's try it. I have the function here next to me. So it's going to be f of, well, it's going to be equal to sine inverse of -9 plus root 2 plus 9 over 2 over square root of 9 minus 9, -9 plus root 2 plus 9 squared minus 2 minus 2 squared. Can't get the square root right. Ln root 2, or sorry, ln absolute value, -9 plus root 2 plus 2 plus 7. So this simplifies to sine inverse root 2 over 2 over root 7 ln root 2, and this will simplify to pi over 4 root 7 ln root 2. And there's your simplification. Okay. Well, it's 10:18, so that's probably it for today. that's the session for today. Thank you guys for, sticking here for a whole 5 hours. Hopefully you found some use in it, and hopefully it was some good studying.
Actually, like, because of you guys telling me that the grades are out, I just have to look at it and see that there's a problem. So that's one plus. I'm gonna bother Professor about it. Also, Adam, the thing came in the mail today. A new calculator. I don't think I've been.
Oh, really?
I don't know,
Yeah.
learning to because I was so excited when I saw it. I was just like, yo, it's a pretty good calculator.
Yeah, this one? Like you got the one that I said?
Yeah,
Told you?
yeah. I was just like,
Is
oh
it
my
incredibly
gosh.
sick? Is it incredibly sick?
Yeah, it's just like it's like getting a new phone. It's like
It is.
But it just does so much.
Yeah.
All right. I still don't know how to get to radians though. I've been trying to.
You do shift. Can you see here?
You can just say it.
I'll just put it. Oh, here. You do shift.
You guys talking calculators?
Menu.
Yeah, we got. Yeah.
Click 2. 2.
Oh, 2.
And then 2 again.
Oh, dude, there's even gradient, dude. I haven't seen that in like ages.
Yeah.
Okay.
It's all the above there.
Calculators.
Yeah.
Yeah.
Now we have.
Now we're engineers because we're getting hyped up on calculators.
Yeah, 36.
Dude, there's an engineering
I can finally do complex numbers, dude. This is.
I'm not even joking. It's there.
It does calculate very nicely.
Is it just
Sorry?
fancy? Is it some fancy $300 one?
It's pretty good for $30.
It's $30. That's it. It's $30.
Oh,
It's like
as it is. I want to get a graphing calculator.
Me too.
Dude,
Me too.
I just want to have one.
Me too. Let me show you. I want to show you one of them that I want to get. Casio, class pad. This is definitely not like to bring to Ryerson because they're not gonna allow me to use that on like tests.
Dude,
but it looks like
how to
this.
cheat on a test, you just buy a graphing calculator.
Yeah.
God,
that's a phone, bro.
It can
yeah,
do.
you think you have a strong
so many
calculator
That ain't no
now,
calculator.
dude.
That's photo math
These
right
ones are
there.
like next level.
Yeah, we need that. We need that for
Oh my
just.
God, it graphs 3D?
It's a multimeter.
It graphs.
No, that
Yeah,
can't
it
be
does. It does like it connects to a
What?
multimeter. It connects to a multimeter, I guess.
What?
It like and it has like a stylus and it does like Taylor series and it does like all this kind of like you can see a bunch of information
Dude,
here.
I'm gonna
used to
buy
be a chem
one.
lab
I swear.
grade
How
8.
much are they? Where's the
Yeah.
price here?
Oh yeah, that's a kind of a separate issue. So if I look at this one's expensive. Let me see if I can find a somewhere
Too expensive to buy the best calculator.
Okay, I mean, if they don't show you the price, that's not a good sign.
It's not a good sign, and it's
not an
correct.
advertising point.
For
That's not a
sale.
selling point here.
We had similar ones in high school, and like you could like plug in like multimeters and different sensors, and it would graph them and give you a function for that graph.
Yeah, that's really good.
From the sensors, it's crazy.
Currently, it's so popular you can't even buy it.
Our teacher said it was $500.
Yeah, it's about that much. It's about that.
I would get if I'm actually gonna get one, it should probably be a used one because
yeah.
I don't know if I
Here's
can
a used
afford
one for $135. That's not too bad.
If you're looking for something AP approved, like you can use it in Ryerson for the exams, try TI 36 Pro. It's a Texas Institute.
I thought you can't use any graphing calculator for exams.
Oh, no, it's not a graphing calculator.
This one's allowed though too. So if you want one that's allowed, like this one's very good.
Yeah. You definitely need one that's gonna be allowed. Otherwise,
yeah.
What is the one that you have called again?
Here, I'll show you. It's a Casio FX 991EX.
Because like the worst thing happened to me in the physics exam. My previous calculator just died, like stopped working. First question in, I died inside. It was horrible. I had to use an online.
$30 for it all. I remember I used to have a $30. I have the one I have right now is $30 too, but like doesn't do as much.
Is it a sharp one?
It's Casio.
Oh, it's Casio. It is
no,
Casio.
It's Casio. Yeah, it's Casio. It's something. It's similar to this one. It's like Casio 99 something. It's not this one though.
Yeah, this one's very good. It does like everything.
I have the sharp one, and I haven't found something I can't do with it yet. Although
Really? Yeah.
it says it has a calculus button. I don't know. Oh no, this has calculus too. There's a DDX button.
And an integration one in the series
it has the same
I
thing.
had one more question though. Like there was this part. It doesn't have like which we're gonna use is the what's that called again, hyperbolic. Like I didn't see that option. Like in my previous calculator, there's a hyperbolic section. I don't.
Maybe like maybe you have to click something though. Like there's so many. There's so many menus.
In a mode. It might be in some mode.
I think this is the first type of like device that you'd actually need to read the manual for.
Yeah.
I'm on campus, right? There's this girl on she gave me my mail and I was so excited.
Yeah.
And she saw me and I was just like, God, now I see why engineers are just like so lonely. She's just like, you're excited for a calculator? And I was about to talk to her about the calculator, but then I saw how disinterested she was. I was like,
so you're like, nah, I'm not gonna bore her with this. Yeah.
Dude, I just realized my calculator has a button called math.
Yeah.
What does that do?
I like that. It just. What do you mean? What do you mean? It makes it do math. Okay, that's what it does.
It's math.
Okay, I have a button called logic, so I don't even know.
That's true.
Okay.
More abstract.
I have a button called Cal.
Wait. Does the Casio one have like XOR and does it have logic gates?
No, it doesn't have logic gates. Maybe in a mode again. Maybe in a mode.
I'm pretty sure it's there somewhere.
Logic gates? I just realized that might mean logic gates. That
Wait,
makes
what's engineering symbol though? Engineering symbol.
Probably just means you're like it changes the way the units are written.
Oh, I thought it meant everything meant equal to 3. Like
yeah,
5.
everything's estimated.
Everything's dang. But
I've never been able to figure out what the M plus does and M minus. I understand I could just look it up, but I've never gotten it to actually work. Like it just
isn't like the alpha A B to F like to store values, like to store.
Save the results of your calculation, and it keep add up your calculations together. When you hit M plus, your last result will be add up to the.
Yeah, you see how you have A, B, C, D, E, F, X, Y, and like in red. That's like you can store answers and values there.
Yeah.
Store a value.
I've never really gotten it to work, but I'll figure it out for sure. There's 2 different X buttons. I'm just realizing.
Which one?
There's an X right underneath on and an X right above delete in red.
No, that's X. That's for storing. That's to store to store a value.
But I've gotten this X to work too as storing a variable, the one under on. I've gotten that to store a variable.
That might be that X might be used for a further like a derivative or something. Like it might be special memory slot.
There's also an estimation thing.
The one I just sent, it does cross product as well.
Oh, you sent
which one?
something?
Have cross product, dude. I would want that.
I like that.
The one,
Yeah.
which one's
It's
that?
so hard. You have to enter all values.
Oh, this wait, does this do
No, but
cross
you can
products?
do that on Casio because if you have a matrix mode, it's the same thing.
It does. It does. It does. It's. I just don't remember where.
Someone
I
said
saw
my
it.
name. Yeah.
Yeah, I was just gonna say, are you doing any more sessions?
No, I guess not, because I was gonna do an ELE one, but I'm just not gonna do it tomorrow. So I just don't have time to figure it out. So yeah, this is actually the last session of first year.
We're
I just
talking
realized.
about players.
This is the last session.
First year engineering done.
First year
Check.
engineering done. Well, 2 more days. We have 2 more days, and then we can say
Two
that.
more exams. Yeah.
2 more
All right,
exams.
thank you so much for the semester, man.
Yes, of course, of course.
Bro, I
I'm happy to
can't
help.
with you.
Yeah, next year it gets a little more confusing because we're not all gonna have the same courses.
Yeah, it's okay.
But the math course we can do together. For most
But I
of us.
realized
For some of us.
BME
mostly.
Which
BME
math
does-
are you taking?
Sorry.
425 or 412?
It's not. There's no 412. There's 312 and 425.
Yeah, I take 312.
Oh, sad.
I think.
425.
Wait, who takes
comp, right?
425?
I am in comp. Is that what your question? Yeah, I am in comp.
No, I was just wondering because when I looked at it,
Is it the same topics that they teach in both classes?
Yeah,
I think just one.
Okay, then maybe it would work out anyway.
It probably
Yeah.
would. What was
There was
it?
just one thing that was
425?
different.
One thing that was different. I heard that too, right? Yeah.
I didn't like that I saw that you guys had mathematics and engineering. I don't see that for BME. I was just like, well, why? Maybe I just missed it though.
Do I have mathematics and engineering?
I think so.
As a course, when?
I don't think I've seen discrete math for engineers.
This not discrete for engineers. I didn't see that for. I didn't see that for.
Everyone takes that. That's gonna be.
I think everybody takes it. Yeah.
Unless I must have been blind because I was just like,
math
huh?
is like math is what would you call it? Practical math, if that makes sense.
And I think I'm not. I don't think I'm doing solid state unless I actually ask to take the
No.
course separately.
I am taking solid states. Yeah.
Yeah,
Yeah,
just
you,
they just.
you take 312, Joshua. You take 312.
Yeah, yeah. I know.
Yeah. Yeah. No, actually, you don't take discrete math for engineers.
Yeah, and I was just like, why?
I'm surprised.
It's
Oh,
called
yeah,
for engineers. Why would that not be a?
Yeah, I think they either call it something else, but I'm gonna take it. Maybe there's something wrong with the, because even CEN they said that we all take it. So I was like, why is it not here?
I don't know.
Maybe it's just a mistake. I don't know. Yep. But I
See
did.
you guys. Good luck on the exam tomorrow.
Good luck. Yeah. Good luck. Good luck, everybody leaving. Yeah. Have a good night. Have a good.
Good luck, everyone.
Oh wow, you're liberal. You actually have a specific list you have to choose from for liberals.
Yeah.
I did not know that.
Not technically liberal if you give me specific courses.
No,
It
I
has-
mean, you can do the other ones. You can do the other ones in other years though.
Oh, I figured out what I'm gonna take as my minor. It's pretty
What are you
good,
taking?
and it involves
You're gonna
solid
minor
state.
in something.
You can take a minor.
I'm minoring in too.
Yeah, it's you just have to take getting a minor is literally just taking specific courses.
Yeah.
Yeah.
But it's 6 courses. You have to
And I'm-
take 6 courses. You have to take summer. Each summer you have to take a course.
Yeah.
Yeah,
Or
but-
you can fit it into your schedule
You
too.
want
But yeah.
Alright,
Man,
good
I
luck.
did
everyone.
not
Thanks, Adam.
Good luck.
for a
Good luck, everybody. Yeah.
minor.
Bye. Good luck.
Everyone who's, yeah,
What are you minoring in?
Me?
me.
Either.
Joshua, you go first.
Oh, I'm gonna do it in medical physics.